ladies and gentlemen. Welcome back to the Future Science Prize Week and the 2023 Future Science Prize Symposium. This session is computer science session. It will be focusing on artificial intelligence. Because we have some seats in front of the stage, you are welcome and recommend you can sit closer in front of the stage. Then you can have the closer interaction with our guest speakers. And now may I introduce this session's convener, Professor Martin Wong. He is the Provost and Chair Professor of Computer Science of the Hong Kong Baptist University, ACM Fellow, IEEE Fellow, and HKAEC Fellow. Let's have a warm welcome to Professor Martin Wong.
Good afternoon, distinguished guests, ladies and gentlemen. I'm Martin Wong, Provost of the Hong Kong Baptist University. Very happy to see all of you here, this wonderful symposium. I feel really honored to be the chair of this session. We have 4 distinguished speakers. 2 are from unicorn companies in Hong Kong. And then 1 is actually a very senior academics, 2 senior academics in the United States. The first speaker would be Professor Huang Xiaogang. So he is a professor at Chinese University of Hong Kong, but most importantly, he's actually a co-founder and also chief scientist of SenseTime. He also the president of the Intelligent Automotive Group at SenseTime. We all know at CHK, Professor Huang is a prolific scholar, researcher. His, according to Google Scholar, his H-index is 145, which puts him number 37 in the world in computer science. So this is exciting that we'll hear from him on AI. Second speaker is Jeanette Wing, Professor Jeanette Wing. He is the Executive Vice President for Research and also Professor of Computer Science. Professor Wing also spent 5 years as a corporate VP for Microsoft Research. And he also served 2 terms as department head of, I would say, in the US, the top computer science department is from CMU. And she actually was the department head for CMU for 2 terms. So Professor Wing will be speaking on AI on the trustworthy side. The third speaker will be Professor Jajaya, also a distinguished professor in the Chinese University of Hong Kong. But again, the most important thing that I want to mention is that he is the founder of SmartMore. SmartMore is an AI base for manufacturing. Professor Jia is going to speak and give the third speech. Last speech will be given by Professor Wenmei Hu. Professor Wenmei Hu is my colleague at UIUC, and he is well known in the computer architecture. So he was a chair professor at UIUC. He retired, and he joined NVIDIA. You all know NVIDIA is a very important, NVIDIA's GPU chip power AI today. So we are very happy to have 4 distinguished speakers. Now it's actually the time for us to hear from them. Thank you very much.
Thank you so much. Thank you, Professor Wong. Please be seated. Now I'm going to introduce our first keynote speaker is Professor Wang Xiaogang, Professor, Department of Electronic Engineering at the Chinese University of Hong Kong, co-founder, chief scientist, and president of the Intelligent Automotive Group at SenseTime. He's going to share with us about empowering future through innovation from AI towards artificial general intelligence. Let's welcome Professor Wang.
Thank you, and thanks Martin for the introduction. And good afternoon, everyone. It's my great pleasure and today to share our research work and artificial general intelligence and foundation models, which is the focus of current AI research. So I got my PhD degree from the Artificial Intelligence and Computer Science Lab at MIT. So and also in 2009, I joined CUHK. In 2014, together with Professor Tang Xiaou, we established SenseTime as an AI company to try to have the AI research apply AI research work to industry, and have been work for years. And for some time, it was successfully got listed at the stock exchange of the Hong Kong on the last day in 2021. And currently, I have over 6,000 employees, and the business cover smart business, smart city, smart life, smart auto, different areas. And also, in last year, the chairman she visited Sense Park and also went to the booth of SenseTime, gave us a lot of encouragement. And also in 2018, and is the Minister of Science and Technology of China, and award this SenseTime as the National Open Innovation Platform for next generation AI on the intelligent vision. And also this year, our CEO and also together with Hong Kong Chief Executive, and together visit the Middle East and have the joint venture with the Saudi to expand our business. And so we got a lot of support from the government and also from Hong Kong. And in the meanwhile, we established in 2018, founded the Global AI Academic Alliance, and to encourage the global research cooperation. So in that year, there are totally 19 members in this alliance, including all the top universities in Hong Kong, the MIT, and Sydney University, and so we want to, and also a lot of top university from the mainland, and to encourage the exchange of the research works. And so today we're going to share about the artificial general intelligence. Actually, I think in the past 10 years, if we give the review of the development of AI, starting in 2012, and a lot of AI research work, they start to pass in the red line of industrial applications. From there, there's a lot of AI applications in different scenarios, different domains. But for different research, different tasks, it requires training different AI models. For example, for SenseTime, in the past several years, we deliver more than 30,000 AI models for business usage. And it means that we need a lot of researchers and to develop a lot of AI models, which is costly and also take a long time to deliver such model. So if you ask the AI researcher whether you can accomplish a certain task, in many cases they will say, okay, yes, but I need a lot of data. I need several months to train a new model for you. And so this is a major limitation for AI to have the scalable applications. But starting from in the end of 2022 last year, and the ChatGPT, they can try to have the major breakthrough, have the new paradigm for AI. And basically, based on a very powerful foundation model, this single model, they can solve a lot of open tasks. We don't need to build a lot of different models. So we call this artificial general intelligence. And this is a very important breakthrough and make this AI application scalable. And this is an example how this different from the traditional AI and AGI. And so, for example, give you the example in autonomous driving scenario, if we have the picture, let's see on the left, and then we want to take certain action for the vehicle. And in the previous AI system, we have a number of defined tasks. For example, we first need to do the object detection to get a bounding box of the objects, and then we have the traffic sign to have the OCR to recognize the words in the bounding box, and then we have the decision-making module, and to make the decision whether we want to slow down or not. So in this pipeline, all these modules, they are predefined. They are all predefined tasks. But for the AGI, basically, you have the very powerful the foundation model. Basically, you can ask any questions about this image to these foundation models. So you can ask. What's the significance of the image and what we should do? And then this model will give the explanation about the content of the image, and also have the logic reasoning, and to give the sequence of answers and take the actions. So this is quite different from the previous AI system, which are all predefined all the components. And we all know in the AI previous AI system, we have the closed data loop. Basically, we have the terminal devices, and it like mobile phones and like vehicles, and it will generate a lot of data and send the data to our model. And then our model also enable the intelligence to the terminal devices. And in the meanwhile, we need to annotate the data, use the data to upgrade the model, and we call this as a flight wheel. And but in the for the AGI, and this is a kind of a new way to generate the content. So we have the powerful foundation models, and this model will have the interaction with a human. It aligns with the human intention, and also give the prompt. It can unlock a lot of new skills of this foundation model. In the meanwhile, this foundation model will generate a lot of useful content with wisdom. And this kind of we call this flywheel to generate the wisdom. And this is a new way. So when we have more interaction with the model will generate more content, and also use the more content to further make the foundation model stronger. And this also gives the new way and to save a lot of industrial tasks. Because previously we let's see the AI software probably can help us to solve 20% of the task, and we need to build a lot of models for specific tasks. But now we are based on the large, powerful infrastructure, and we build a single model and a foundation model, and this foundation model they can also can adapt to different vertical domains, and to solve a lot of open tasks through the fine tuning, and which is much more efficient than before, and it can save 80% of effort. For example, nowadays we can use the foundation model to help us to improve the programming, and it can the programmer make a 20% effort, and the foundation model can automatically generate a lot of code to help the programming, largely improve the efficiency. And this is also make the model as a service possible, because previously we also hope that we can use a model as a service as a business. But on the cloud platform, we have to serve a lot of different models, and also for a new task, you always have to try to train new models. So this kind of becomes impossible for model as a service. Also, it's not efficient. But now it's kind of different. With a single foundation model, we can serve a lot of different tasks like ChatGPT, GPT-4, and so this make this as a possible model as a service as a possible. So like for example, GPT-4 itself will become the product and to provide a lot of service. So this is going to largely empower the industry to make the AI industry market grows fast, and also it's very useful for the AI to try to have this handle this fragmented industry market. And very importantly, in order to achieve these very powerful foundation models, and there are several important factors. For example, we need a lot of massive, clean training data and very high computation power, and using the algorithm, and also a lot of engineer efforts. For example, this for ChatGPT, it uses 45 billion pre-training data with over 500 billion tokens to train the model. Currently, we are using the 1 trillion level the tokens to train even stronger foundation models. And also, we need thousands of high-performance GPU cards like A100 to train the models. Let's see, now I think it's a skill even scale up to let's see the 10,000 and even larger number of GPUs. It's need a very powerful infrastructure on the super computing clusters. And also in the I think in the past several years, OpenAI they work on the GPT models, and from small to bigger ones, and they accumulate a lot of engineering know-how. So this know-how is also very important. So if you want to train a large foundation model with with 100 billion parameters, it's not easy to be successful at once. You need to accumulate a lot of know-hows before that. So with our infrastructure, so in the past several months, we trained over, let's say, 10,000 models, like let's say 1 billion parameter levels. And we train over 100 models with 10 billion parameters. And this large number of trainings on these models help us to accumulate a lot of know-hows. And for some time, we have our foundation model system. And actually, we start to work on this foundation model since 2019. And first, we work on the computer vision models. And our first computer vision models for face, and it has 1 billion parameters. Last year, we have our largest, most powerful computer vision model with 22 billion parameters. We also work on the foundation model with natural language processing, and since 2021. And so currently we have several NLP models with, let's see, over 100 billion parameters. And also for multi-modality models, in March of this year, and we open source 3 billion multi-modality models, and that's open source. And currently, we also have even more powerful multi-modality models with 20 billion parameters. And we also have the AIGC models given the language description to generate image and videos. And also we have the model for the decision making using natural language to make the decision, do the planning, to solve a lot of open problems. So these AGI models, they cover the computer vision, natural language processing, multimodal, and the AIGC, and also decision making, different aspects. And in order to accomplish this, it needs very powerful infrastructures. And so in Shanghai Lingang, we built up a powerful computing cluster with 6,000 petaflops and computation power. And now it can simultaneously training 20 foundation model with parameters like 100 billion, these kind of levels. And also this, based on this, it will train the language model and the AIGC model, the multimodality model, and the digital human, and large 3D space reconstruction, and 3D object reconstruction, different model size. Here is an example that we use our language model we call SenseChat, which has 123 billion parameters. And we have a lot of different benchmarks. And we compare this SenseChat with ChatGPT and also GPT-4, also Llama 2. And here you can see that this SenseChat, they will auto-perform the ChatGPT, and also it can approach GPT-4 on certain benchmarks, and also at certain dimensions. And so we hope that we will reach the GPT-4 level by the end of this year. And also, this language model can support a long context window with 32K tokens. Basically, it means that you can give the long input to the language model. For example, you can give the article or even a book and as input to this model. Or you have the hundreds of rounds of dialogue as input to this language model. So this language model can take a longer input and can have the more comprehensive understanding. Because previously the language model only have the 2K token length as the context input, but now it's significantly improved. Here example, we take the one paper as the input, and then this you can ask any question to the model regarding to this paper. And also this can be used, let's see, can be used as improved programming, and it can improve the efficiency of the programming at 27%. And also on the benchmark, the human evil benchmark, it's the one pass successful rate of this our model is 68%, which means that you write the code and on 60% of the chance is completely correct, and so this have the similar performance as the GPT-4. And we are currently our programmers using this to improve the efficiency. We also promote this to our customers. And this language model can also be used work as an AI operation system, and it can control other functions, other apps, because it has very strong reasoning, decision-making capabilities. And also for the AIGC, we have the Sense Mirage, and to use based on the text input to generate the visual content. We keep improve the performance and the capacity of this AIGC model. Here you can see we have the different versions, and the quality of the image has been improved significantly. And for the AIGC, we know that it's very important to design the prompt as the input. And so the professional prompt will be able to generate even higher quality image. But usually the normal users, they don't know how to make the professional prompts. For example, on the left side, and we give the input from our normal users. And based on our language model, its capability, it will automatically expand the simple input prompt to the more professional one, and then it can generate much higher quality images. And also given a few images for myself, and we as the input of the model, it can generate a special model for myself. Here I give the example. I give the 20 pictures of myself and trained LoRa, and which is a specialized model for me. And then you can input the text to generate my images in the future, or even my videos under different scenarios automatically, which is quite useful. And this is the product we promote in Germany Auto Show. So basically, the human can draw the sketch. You can see this the outlier, the sketch, and also you can give the input what kind of picture you want to generate. And based on the sketch and the text description, and this model can generate high quality the images. And this will be quite interesting for a lot of the normal users, for them to create beautiful pictures. And also for the multimodal foundation model, and so give the image, and you can ask using language description to describe any task, to ask any question regarding to this image. It will have the very rich description and the feedback about the image content. Yeah. So we also have the open source program for smaller foundation model like the 7B or 13B parameters, and we open source to the public, and it has a high performance, and also can help the research community and to explore a lot of applications. And then the last part, I will quickly see a few, for example, in the autonomous smart vehicle, and how this the AGI foundation model can improve the autonomous driving and the intelligent cabin with the AI as a cloud service. For example, for the smart cabin, we hope that it can become a smart travel assistant. And because inside the car, there's a lot of sensors, and this multimodal large model can combine these different types of signals to comprehensively understand the need of the passengers. And this language model can serve as the brain of the cabin to control different devices, applications inside of the car. And also for each passenger or the driver, we can have the memory, and this memory can be attached as a document attached to the foundation model, and then this foundation model can be personalized, have the personalized interaction service for individual person, and also the AIGC model can help to create the customized digital human, and this cabin brain will be able to connect with on the vehicle side and receive a lot of different types of signals, and to have the connect with the memory models, and to understand the status of the vehicle. And on the cloud, we have a lot of foundation models to empower this brain. And then at the application level, it can support a lot of applications on the safety, entertainment, education, and the efficiency. And based on the foundation models, we have developed a lot of interesting applications. And here I give a few examples. One example is like we use as a health consultant. So basically inside the cabin, we use a sensor. We can measure the breath rate, the blood pressure, a lot of measures from the passengers.
Such as difficulty breathing, dizziness, and so on.
Feeling a bit tightness in the chest, having trouble
And
breathing.
then this foundation model can proactively kind of initiate the conversation with the passenger. So if the passenger need the help to the calling, to have the emergency call, and or stop the car, or it can provide a lot of consultant regarding to the health to help the passengers. And this is another example as the travel assistance.
Today is July the 7th, and the weather is clear. Do you want to know what significant events have
You can
occurred
summarize
in the AI
the news
field over
of
the
on
past
that
24
day.
hours?
Sure. Tell me about it.
The 2023 World
And
Artificial
if you want to
Intelligence
go
Conference was held in Shanghai
to the
on
certain
July the 6th.
destination,
The theme
and
of this
then
year's
it will
conference
automatically
is Intelligent
generate
World,
the travel
Shaping
plan
the Future.
for you.
I'd love
And
to visit
the
Shanghai.
foundation model also can automatically call
Can you
the
help me with some
APP to
recommendations
book
for
the
attractions?
hotel, flight
Sure,
tickets,
here are some
and
recommended attractions
for you.
to explore. Would
You
like
just
me
need to
assist
confirm
you in
with it.
booking a local hotel?
Sure.
I've selected the most suitable hotels in terms of price and distance for your chosen dates. If everything looks good, please face the screen and say, confirm.
Confirm.
And
Payment
during
has been
the
successfully
travel, and you
processed,
have
and the booking
take a lot
details
of nice
have been sent
pictures
via
and
mobile
videos,
device.
and this model can automatically and help you to generate the vlog, and to help you to distribute with your friends, share with your friends.
Please assist me in creating a travel vlog. Certainly. Make sure to Photoshop me into some of the landscapes as well.
It's all set and
And lastly, for the autonomous driving, and this in the last month, Tesla announced that they're using a single neural network to establish autonomous driving. Because previously there are several different modules like perception, planning, control, fusion, etc. And only the perception part is based on the neural network. So the other parts are based on the rules, and you have to hard code a lot of things. But with a single neural network, currently people can have the end-to-end autonomous driving. It will be driven by massive data, and this also requires this one of the important application of the foundation models. So for this end-to-end driving, we can see that the performance at each individual different modules has been improved a lot. And so with the foundation model, so you can only, we can establish the autonomous driving only based on the cameras, and also without require high definition map. And it also have the good interoperability, interpretation capability, and the safety. We can also upgrade the model efficiently. And so this foundation model, the AGI, will be very powerful to empower the intelligent vehicle. So we have a good intelligence driving experience. And this is only the one of the example of AGI in the industry vertical. Actually, currently we are applying this to a lot of industry domains, and they give us a high expectation, and we hope that we can a lot of talents work together and to create the beautiful future with AGI. Okay, that's the share, all my share. Thank you.
Thank you so much for your interactive sharing. Please be seated. Our next keynote speaker is Professor Jeanette Wing. She is the Executive Vice President for Research and Professor of Computer Science at Columbia University. She's going to share with us a trustworthy AI, even though she can't join us in person, but she has recorded the video to share this topic. Please enjoy.
Thank you very much. It's an honor to be able to speak at the Future Science Prize Symposium. I am going to talk about trustworthy AI. I am the Executive Vice President for Research and Professor of Computer Science at Columbia University. I'm also an Adjunct Professor of Computer Science at Carnegie Mellon University. The talk I'm going to give on trustworthy AI is divided into two parts. The first part, I'm going to explain what I mean by trustworthy AI in the context of trustworthy computing. And the second part of my talk, I'm going to propose one way in which one could try to make an AI system trustworthy. And that way is using formal methods. It's just one of many ways that we might want to make an AI system trustworthy. So let's begin. We already know that for certain tasks, AI systems have achieved human performance. We can recognize objects in the street. We can recognize speech at our home. And in certain tasks, AI systems have exceeded human performance. So as many of you know, AI systems have beaten the best human Go player in the world. And the same is true for many other games. The promise of AI is huge. They will drive our cars. They will help doctors diagnose patients better and more accurately. They will help judges make more uniform court decisions. And they will help employers find the most suitable job candidates for their positions. course, the most exciting advance in AI occurred very recently, and that is with large language models, or more generally, generative AI. And we already know the potential of large language models of helping everyone in whatever job they do, for summarizing information, for creating new information, and for helping humans do their job. But there's a big question. Why should we trust AI-based systems? If we add duct tape to a stop sign, we can fool an image classifier into saying it's not a stop sign. If we add noise to an image, they classify a benign skin lesion as malignant. We also know from studies that have been done by the media and academia that AI systems that are used in the US court system can be racially biased. And we have heard, also reported in the media, that companies that try to use AI systems for hiring decisions have been biased against women. And of course, we also know that this wonderful technology that emerged in the past few months, generative AI, large language models hallucinate. They confidently invent information that's not true. So there's a question is, how can we deliver on the promise of the benefits of AI, but address these scenarios that have life-critical consequences for people and society? In short, how can we achieve trustworthy AI? And now I'd like to put the term trustworthy AI in context of a term that the computer science community has been using for decades, called trustworthy computing. Trustworthy computing has come to mean certain properties that we would associate with a computing system. Trustworthiness for a computing system means reliability. Does it do the right thing? Safety. Does it do no harm? Security. How vulnerable is the system to attack? Privacy. Does it protect a person's identity and data? Availability. Is the system up when I need to access it? And usability. Can a human use the system easily? And by computing system, I mean a piece of hardware, a piece of software, and the people who might use the combination of hardware and software. For trustworthy AI, we're raising the bar in terms of what we mean by trustworthiness. Of course, we want a trustworthy AI system to be trustworthy in the sense of traditional computing systems. We want AI systems to be reliable and safe and secure and so on. But trustworthy AI adds new properties of trustworthiness for us to consider. Accuracy, robustness, fairness, accountability, transparency, interpretability or explainability, and even ethical questions. And AI systems also are a little different from the kind of computing systems we've focused our attention on in the past. In particular, one can think about an AI system as not just a piece of code like the machine learned model, but the data that was used to train and test the code, and the data on which the model is going to be deployed in practice. And then for many AI systems, as I alluded to in my opening remarks, there's a specific task that the system is supposed to perform. So one can think about an AI system as everything a computing system is, plus data and a specific task. Now, what about these properties I've just introduced? Accuracy is perhaps the gold standard for machine learning. How well does the AI system do on new, unseen data compared to data on which it was trained and tested? Robustness. How sensitive is the outcome to a change in the input? Fairness. Are the outcomes unbiased? Accountability. Who or what is responsible for the outcome? Transparency. Is it clear to an external observer how the system's outcome was produced? Interpretability or explainability. Can the system's outcome be justified with an explanation that a human can understand or that is meaningful to the end user? And for ethics, was the data collected in an ethical manner? Will the outcome be used in an ethical manner? And ethics is a very difficult property to strive for an AI system, because ethics may be culturally dependent. It may be locally dependent. It may be dependent on a community. So whether a question should be answered yes or no may differ depending on who you're asking. And even properties like fairness are not easy to define formally. And there are many notions of fairness that have formal definitions, but are actually in contradiction with each other. So these are new properties that we have to worry about when talking about trustworthy AI. And they're challenging properties to formally define. But these are the kinds of properties end users want of AI systems. And businesses, the customers for any company will want AI systems that that company produces to be trustworthy in these manners. So the question I pose the community, the computer science community, is how can we achieve trustworthy AI? One approach is through formal methods. So I want to now put into context traditional ways that one might use formal methods to verify a computing system satisfies trustworthy computing properties, with how we might interpret that framing for an AI system with respect to trustworthiness properties for AI systems. So let's start with traditional formal verification. There are three components in the red box. It's read M satisfies P. M stands for the system, the AI system that or the computing system that we want to show satisfies a particular trustworthiness property. M could be a piece of code, could be a program, or it could be a high-level protocol specified like as an algorithm, or it could be an abstract model of a concurrent or distributed system. In the end, M is a mathematical object. We can reason about it, we can manipulate it, we can build these objects to scale so that we can automate our reasoning about M. P stands for the property of interest that we want to show of M. P will be our expression of the trustworthiness property we care about. It could be a security property, a reliability property, availability property, and so on. And many decades of research have gone into just the ability to express P and to classify the different kinds of P's we can express in different kinds of logics. So P's usually written in some kind of discrete or Boolean logic. And the kinds of properties we care about for verification are usually divided into what we call safety or liveness properties. So reliability is a safety property. Availability is a liveness property. And finally, we have the double turnstile symbol, which is read as satisfies from mathematical logic. M satisfies P. Satisfies, this double turnstile, connects the model M with the property P. It really can be viewed as a logical framework for reasoning about whether M satisfies P, whether the property P holds of every execution of M. And again, decades of research have gone into inventing logics so that we can do this reasoning, building computing tools so that we can do the reasoning automatically and to scale. And the kind of tools I'm talking about are model checkers, theorem provers, and satisfiability modulo theories, or SMT solvers. Now, very often, we also add a fourth component in our reasoning for traditional formal verification, and that is what I call E. E stands for the environment in which the system, represented by M, will operate. So you can think about E as the physical environment in which you put the computing system, or you can think about E as the operating environment, like the operating system, for a piece of code that's running on your computer. E is another way to capture formally the assumptions that we make about the environment in which M runs. Now, what about verifying AI systems? How do we reinterpret E, M satisfies P for verifying AI systems? And again, we need to raise the bar. First, let's reinterpret M. M can still be a piece of code, but more likely, M is a component of an AI system that is learned by a machine or machine learned model. So what's different here is that for a computing system, it was a human being who produced the code. For AI, it's a machine that produces the code. That's already one difference. Now, P is going to be one of those trustworthiness properties I mentioned earlier for AI systems, not just safety and security and reliability for computing systems, but properties like robustness and fairness and interpretability for AI systems. Expressing P, those new kinds of properties, will very likely need new kinds of languages, new kinds of logics, probabilistic or stochastic in nature. And finally, we have the double turnstile that connects M and P. And here again, we may need new kinds of logical frameworks to allow us to reason about M and P. We may need new kinds of algorithms to do that reasoning because we're operating over continuous variables or reals, not just discrete variables or Booleans. So interval analysis allows us to reason over intervals of reals. And the most important difference between verifying a traditional computing system and verifying an AI system is D. D is the analogy to E in the traditional verification of computing systems. D here stands for the data, the model of data that we use to test and train the model M, but also the D stands for the data seen by the machine learned model that it's never seen before. The real world data that the model sees or the AI system sees when it's actually deployed in practice. So there's a challenge here of how do we specify D? How do we specify the model of D in a formal way? We could, for instance, use stochastic processes or a distribution that generates the data inputs on which M's outputs need to be verified. But this is a research question, a research challenge. So in a nutshell, when I say, let's try to use formal methods to verify that an AI system is trustworthy, this captures succinctly what I mean. And now what I'd like to do is walk through how we would tackle this from a research point of view. What are some of the open questions and what are some of the technical challenges that arise in the context of trying to use formal methods for AI systems? As I mentioned, there are already two main differences I want to highlight. The first is the need for probabilistic reasoning, and the second is the role of data. And for this talk, I'm only going to talk about two aspects of the role of data, specifying the unseen data and what do we quantify over, to show that there are new questions that are raised by trying to use formal methods for AI. So let's start with the argument for why do we need probabilistic reasoning? And first, let's look at M. M, remember, is different from a typical computer program. You can think of M as a deep neural network, a very large graph with lots of nodes and lots of edges in between the nodes and layers of nodes with edges connecting the layers. M is semantically and structurally very different from a typical computer program. M is inherently probabilistic because internally, the model itself operates over probabilities and outputs results with assigned probabilities. So the model itself operates over probabilities, spits out probabilities. It's inherently probabilistic in a way that a typical computer program is not. Structurally, I already alluded to this difference. M is generated by a machine and unlikely to be human readable. On the other hand, in computer science, we're very good at looking at generating what we call intermediate code, code that machines generate and humans can't read very well. And this intermediate code is something that we're also very good at analyzing using techniques like static analysis and dynamic analysis of code. So it gives me some hope that we can come up with new techniques to reason about this new kind of intermediate code. A machine learned model is usually placed in a real world situation where there's a lot of uncertainty about M's environment. And the only way we know how to represent uncertainty mathematically is through probabilities. What about P? P, interestingly, may be formulated over continuous, not just discrete domains, and or using expressions from probability and statistics. So the very expression of the trustworthy property that we care about, whether it's fairness or robustness, may require probabilistic reasoning. And in fact, may require reasoning over continuous domains. So for instance, robustness properties for deep neural networks are characterized as predicates over continuous variables. Fairness properties are characterized in terms of expectations with respect to a loss function over reals. And the only formal notion that we have about privacy is called differential privacy. And differential privacy is defined in terms of a difference in probabilities with respect to a small real value. So even the expression of P requires probabilities, continuous domains, very different from predicates in the past where we would express a trustworthiness property in terms of Booleans, and the answer would be true or false, yes or no. And finally, the logic that ties M and P together will very likely need to draw on probabilistic logics and hybrid logics. Now, the good news is that the formal methods community has been working on probabilistic logics and hybrid logics for decades. So I believe that we need to revisit them and possibly scale them up and invent new verification techniques that can work over reals and nonlinear functions, probability distributions, stochastic processes, and so on. Now, what about the role of data, D? I first want to distinguish between what I call available data, data at hand used for training and testing the model, and unseen data, data over which M needs or is expected to operate without having seen it before. Now, here's the first technical challenge: specifying unseen data. The computer science and formal methods community has never had to do this before. So now there's a new research question on how do we specify D? How do we specify D, or maybe just characterize the properties of D? Well, one approach is to specify D as a stochastic process or data distribution, for instance, via its parameters. So for a normal distribution, you might specify it in terms of the mean and the standard deviation. One can think even more grandly and use a programming language to specify D. So for instance, there are probabilistic programming languages that have been invented. Perhaps the most widely used one is called STAN. And we can use a probabilistic programming language to write a probabilistic program that actually stands for a statistical model. So we can use this program to stand for the specification of D. I'm really suggesting all of this. No one has done this. This is why these are research questions and research directions. But the real rub is real world data. What of large real world data sets that don't fit common statistical models, the ones that you see in your textbook, or which have thousands or millions or billions of parameters? You can't easily just write a specification down for D for those kinds of data sets. Yet these are the very data sets that large language models are operate over and train on. And all of a sudden, we are in a world that the technology has caught up or has surpassed where we are in the science. Now, there's another peculiarity that is a bit of a conundrum, and there's a potential circular reasoning which we need to break. So here's how the argument flows. To specify unseen data, D, we need to make certain assumptions about the unseen data. This is common practice in any approach using formal methods. To specify X, we need to make some assumptions about X. But then would these assumptions not then be the very same assumptions as those we would make to build the model M in the first place? And that sounds circular. Another way to phrase circularity is, how do we trust the specification of D? Remember, our point of this exercise is to say, how can we trust M? Or in fact, how can we trust the AI system that M is representing? But now I've pushed the trust to how can we trust D? So how do we break this circular reasoning? Well, one approach, and by the way, I don't know the answer to this question. One approach is use a completely different set of tools outside of formal methods, outside of computer science. Perhaps a repertoire of statistical tools can help us look at D and ensure that we have the specification of D right. Another more common approach within formal methods is to assume that we have a small initial specification, and it's small and simple enough that we can eyeball it, manually check it by inspection, be confident that it represents the D we want, and then use that specification to bootstrap an iterative refinement process to build up a larger and larger specification of D that represents a larger and larger D. This technique is akin to a technique in formal methods called counterexample guided abstraction and refinement. And finally, I've just talked here about specifying unseen data. We also need to relate, how does the specification of unseen data relate to the specification of the data on which M was trained and tested? Here's the second technical challenge. Again, I don't have answers, I only have questions. In traditional formal methods, we strive to prove for all x, p of x. So in traditional formal methods, if x stands for an integer variable, I am going to prove for all values of that integer variable, I will show that p holds of x, of that value. And if I prove it for all integer values, then I know for sure that any integer value that is taken on by that variable x upon execution of the program, p will hold. I'm fully confident that p will hold because I basically overproved what I needed to prove. The same thing is true as if I'm running a concurrent or distributed system and I'm trying to prove for all executions of the system, p holds. So I might overprove and say for all behaviors of M, which stands for the computing system that I want to show satisfies a particular trustworthiness property, I'll show for all possible behaviors, knowing that any one behavior that is reached through the execution of the system, p will hold. Now, for AI systems, the world is a little different. We do not expect M to work for all input data or for all data sets D. So we can't say for all x, p of x. That's too strong a statement. That's not to say that if we can't say it, then we're in good shape. But in reality, it's more likely that we can't hope to prove for all x, p of x. So what do we quantify over? What do we do? Well, let's divide this expression for all x, p of x into the quantification part and the property part. So p of x is the property specification. It represents a fairness property or a robustness property. And for all x represents the specification of data. And we have two extremes in traditional formal methods where we prove for all x or we prove for some x. Now for AI systems, we already know that we're operating over data distributions. And so we might replace that with for an X drawn from a distribution for all distributions. That would be a very nice property to show, or for an X drawn from a given data distribution. Now, just to be concrete, robustness properties very nicely fit into the category where we might say, for any arbitrary norm-bounded perturbation, which would be the for all D here, if I change any pixel, I can assure that the classifier will still be robust to that change. That's a very strong statement. It's something that we know how to do for certain kinds of perturbations and for certain kinds of objects like images. So robustness, I have some hope that we can actually use formal methods successfully. Fairness is harder. What do we have? Today, we can, for a given single data distribution, show that for a given fairness property like statistical parity, we can show our classifier is fair. Traditional example that people use in looking at fairness properties and fairness machine learning algorithms is the recidivism data set that was used to show that risk assessment tools used in the US courts are racially biased. So on the one hand, we have robustness which lends itself to something akin to for all. And on the other hand, we have fairness properties which lends itself to something more akin to for a given data set. But what we'd like to do is perhaps something in between where we're showing for a class of data sets, P of X holds. So for instance, for robustness, instead of changing any old pixel and saying for any arbitrary norm-bounded perturbation, we might want to say for a particular semantic perturbation or structural perturbation, robustness will still hold. And so the class of distributions would be within the class of semantic or structural perturbations. Similarly, for fairness, we don't want to show a classifier is fair with respect to a single distribution. We'd really like to show that it's fair to not just that distribution, but for nearby distributions. And that would be then the class of distributions over which we would show that fairness holds of a machine learned model. So let me be a little more concrete. I've already alluded to this, but what we like to be able to show, for instance, for robustness in the adversarial machine learning setting, is that M, the machine learned model, is robust to all norm-bounded perturbations D. But more interestingly, we might want to show that M is robust to all semantic or structural perturbations for the task at hand. And now let's consider computer vision. Imagine you have a computer vision system in your self-driving car. And the car is driving itself on the road and it sees a car in front of it. And there's a dent in the back bumper of the car. Well, you still want the computer vision system to classify that car in front of it as a car, even though there's a dent in the bumper. And a dent in the bumper on an image will not be any old pixels changed. It will be a localized set of pixels that are changed from a normal bumper. So we want the classifier for the self-driving car case to say it's a car, and it's a perfectly fine car. However, if the task is repairing the car in a service shop, then you want the classifier in the service shop to say a repair is needed to this bumper because there's a dent in it. So in that case, that bumper for that car should be classified as it needs to be fixed, not that it's a perfectly fine car. So this is where task specificity comes in. And this is partly what I mean by semantic or structural perturbations. As for different property fairness, we might want to show that the machine learned model is fair on a given data set and all unseen data sets that are similar for some notion of similar. So a few years ago, some colleagues and I wrote a paper that appeared in Neurips to show that if you build a fair classifier, the best fair classifier you can build with off-the-shelf algorithms, then it's very easy to change just slightly the coefficients in the given data set distribution, and the classifier will all of a sudden be unfair. In other words, it's very easy to build a fair classifier that is not robust, that is brittle, that is easy to break with very small perturbations to the input set. So that's not good news. What we'd like is to build a fair classifier once and for all and have it work for a class of data distributions that are close to each other. And that's what we did in this paper. We used an online algorithm to build a fair classifier that is robust to a class of distributions. And it's a very canonical approach in using online algorithms. It's inspired by two-player games. Now, I want to also talk about, I talked about M, I talked about P. I want to talk a little bit about double turnstile, which is the verification task. How do we check the available data for desired properties? For example, if we want to detect whether a data set is fair or not, what should we be checking of the data set? It's not enough always to check what the machine learned model is. Maybe that's too late by then. Wouldn't it be nice if we could detect whether a data set is fair or not? So when we go through the trouble of training a machine learned model, we know it will be fair. If we detect that the property doesn't hold, like a fairness or robustness property, how do we fix the model, amend the property, or decide what new data we need to collect for retraining the model? In traditional formal methods, when we try to prove that a computing system is correct, we actually almost never prove that a computing system is correct. We almost always find a bug in the system. It could be a bug in the model. It could be a bug in the property specification. And the bugs are actually very, very useful feedback to the designer of the system. We call that bug a counterexample. So the question for in the AI context is, what is the equivalent of a counterexample in the verification of an ML model, and how do we use it? Another question is, how do we exploit the explicit specification of D, unseen data, to aid in the verification task? And finally, we have some standard verification techniques. Can we, like for instance, over intervals, reals, how can we extend these techniques to operate over data distributions? I want to pop up a level and say, I've only talked about an approach of using formal methods, which we in the community would call post hoc verification, where you have a property of interest, you have a model or a piece of code, and given both, you try to show that M satisfies P. There's another approach where you start with the property of interest and you construct M iteratively, step by step, always preserving the original desired property P. This is called correct by construction, and we might also call it as model synthesis. I already mentioned that formal methods for AI would likely have to be task specific until we know how to prove things more generally. It's true that generative AI gives us a hint at general AI, but right now we are still looking at AI systems as being task specific. There's another aspiration that we have in formal methods, which is to do proofs compositionally. That means you have a big system, you prove a property is true of components of the system, and then you infer the property holds of the composition of the components. And so you don't have to reprove the whole big system because you've already done the little proofs. And finally, as I mentioned earlier, there are statistical methods for model evaluation and model checking, which I would encourage the computer science community to pursue by complementing formal methods with statistical methods to validate specifications, be they of the data or the model or of the property. So I'll close here and say that this DM satisfies P is my characterization of how trustworthy AI meets formal methods. Thank you very much.
Thank you so much for the sharing. Before I invite the next speaker, I would like to have an announcement. One of the guests lost their Xiaomi mobile phone in the brown case. If you can help to look around whether you can see the lost phone, if you can find it, please put it to the reception. Thank you for your help. So now we are going to invite our next keynote speaker is Professor Jia Jiaya. He is the Professor, Department of Computer Science and Engineering, the Chinese University of Hong Kong, founder and board chairman, SmartMore IEEE Fellow. He is going to share with us from large language models to large vision language models. Let's invite Professor Jia. Please come to the stage.
I'm pleased to come here to give a talk, and after a very theoretical analysis about the GenAI, you see this is really, really theoretical. So I tried to give you a more relaxing material about what is really the large language models and how can we contribute to the current state of art or construction of large language models. So Xiaogang and me are both from CHK, so you can imagine how strong the AI researchability of CHK is. Okay, just for kidding. So first, I will give you some background about what is really the deep learning and the large language and vision models. So human brain. So I give you some context. So human brain. So what is really a human brain? So this is our biological construction instead of the machine structure of the human-made objects. So in human brain, there are more than 86 billion euros, B for billion, billion euros. So the neuron here, so it's not a very big number. So if you like a number here, so you may know if you have any knowledge about current large language model, you realize so today's large language model easily reaches more than 1,000 billion parameters. So does it mean that the computer is already more powerful or superior to the human ability? The answer is no. Why is no? Because every neuron is not work by its own. It has synapses. Synapses is another kind of connection. It's like a human hand, so connected to others. So when I'm a neuron here, so I have a hand, I will touch the other neuron. So the hands, how many hands for each neuron here? So the number is surprising. So more than 7,000. So that means every neuron has more than 7,000 hands to touch each other. And if we multiply the number here, so 7,000 times the 86 billion, so we have, so the total number of parameters in human brain is about 700 trillion. So this is the actual number about the parameters for human brain, for every human brain. Everybody sitting here, and you should be proud because you have more than 700 trillion neurons in your brain. And I give you a number. So if you don't quite understand this number, I give you a comparison. So do you know the GDP of China in 2022? The whole country. The GDP of the whole country of China is about 121 trillion RMB. So that means this number is already 6 times larger than the total GDP of the country of China. This is just a background. So I give you some background to let you know that actually, so we still have a very long way to go if we talk about human biological thing. And there's another fact. I see some boys and girls here. So if you don't understand this clearly, I can give you an idea. Say when you find a kid at 6 is super naughty. If he's super naughty, this is not because he's naughty. It's because at that time he has the most synapses and neurons in his or her brains. And when he grows up, more and more neurons will be cut out from the brains because they are useless. And then slowly, so when we grow to 20 or 30, so we get a stable number of all the neurons in our brain. And then when we go to the 60 or 80, so we get a minimum number of neurons in our brain because we get old, so a lot of neurons are died. This is the general process of human biology evolution. Now, this is artificial neural network. So it's, you look at this table, you feel like this, okay, it's similar. So we try all the ways. So try all our best to make the artificial neural network similar to the human brain neural network. This is what we did. And it turns out it's very successful, and it proves very effective in finding some great solutions. Now, I can show you this figure here. So in past 20 years, so the size of neural networks determines ability, and this is some facts. So when we just use hundreds, thousands of different parameters in our artificial neural network, we find the computer can only do some very simple recognition, like a handwriting recognition or face recognition, so this kind of a very simple thing. But if we increase the total number of parameters into millions, then we found, okay, suddenly this system is capable of doing face recognition, target detection, semantic segmentation, complex class classification, so on and so forth. So it's kind of already amazing. But in past 5 years, people realize if we do large model, so that means use tens of billions of parameters, then we achieve qualitative change. And this qualitative change is showing on the right figure. So it's more like when the kid is growing up, and in year 1, he or she knows nothing, and year 2, almost nothing, and year 3, almost nothing. And suddenly, in year 4, year 5, he becomes an artist. And this is the change. This is what we observe from the artificial neural network in past 5 years. And when we use tens of billions of parameters in this machine brain, and we realize this machine suddenly becomes an artist. And it started from almost nowhere. And today, he understands almost everything. Here is another example. I showed it in past situations, in other scenarios. So if we use just the 3 billion parameters to ask the system to write a Q data structure using 2 stacks in Python. So this basically means I ask the system to write a program, right? So this is write a program. And if we use just 3 billion parameters, So this is the answer. So this is the answer the system returned to us. So basically, it tells us, okay, you create 2 empty stacks, and then create a new queue data structure by pushing elements. So it's, it's not what we want, because we wanted the code, but this is not a code. Okay, I increased into 30 billion parameters. That means I increased the total number of parameters by 10 times. Suddenly, it gave us the complete code. And there's no any gap between it. That means there's no anything gradually increasing thing, no such thing. This is emergence. This is called emergence. Suddenly, it is capable of giving you the complete code without any error. So this is what we found in past days. And also, this is another example showing by GPT-4. So basically, if you ask system to draw a dog, okay, he can draw a dog like this one to you. Okay, this is a JavaScript, a dog. But if you ask system to write a dog using SVG, then you see this output the code. And if you run the code, and you find, okay, so the code output such a figure, and this figure is more like an abstract dog. And this is the SVG programming language, and you can imagine. So basically, this GPT-4 may not know what is exactly the SVG produced drawn dog, and he can imagine, so this is dog you want. All right, this is called imagination and connection. So what is the current progress of a large language model? It's interesting, though, globally. So we found the GPT-4 by OpenAI has reached more than 1,000 billion parameters, and GPT-5 has been trained over 30,000 and 50,000 H100 GPU cards. And in academia, so we have Llama and Llama 2. And in China, you see you have more than probably 100 companies has products in different large language models. So on the right, you see there are some claim is already useful, almost useful, decided when to useful, and I'm not sure when to get produced. So this is just for fun. But actually, so that means we have really a lot of companies working on the large language models. Then, so the large language model, so how can we evaluate the large language model? So today, so if you look at GPT-4, so basically it contains more than 1,000 billion parameters, and its storage capacity is equivalent to tens of millions of books. What does it mean? So how do you understand this figure? So if we talk about the National Library of USA, and this is the largest library in the world, has more than 180 million books, but GPT-4 contains hundreds of such libraries. So this is the total number of knowledge that current large language model has learned. And this is a huge knowledge. And I believe in the next 5 or 10 years, and there will be no knowledge in human history ever created to learn by machine, because all the knowledge has been learned by a machine. There's no knowledge anymore. This will happen in the next 5 or 10 years. Then I also give you some other facts. So this is interesting facts. So GPT-4 was trained on by a leaking message. It's not formally announced. I'm not sure this is the correct number, but I just guess it's almost this number. So these are 25,000 A100 cards for over 3 months. It costs $900 million if purchasing the hardware. So that means anyone want to reproduce the GPT-4, okay, at least you need to have, in the first place, you need to have $900 million to buy the hardware. Then you need probably another hundreds of millions of US dollars to hire the person to do the deployment. So it's very, very expensive. And even using the OpenAI clouds, training costs will be $63 million. That means if I don't buy the hardware, okay, then you can hire. So you can hire or you can rent some machines from a cloud. It also costs you $33 million. It's still very expensive. And there's fact interesting I give you. So according to the GPT paper, so there's a paper from GPT, and engineer ever discovered a data division bug. I mean, this is something wrong. I mean, this bug during training. But because this is so expensive, and even the OpenAI cannot afford a retraining system, so they choose to take a turnaround to let the bug exist there because it's too expensive. Okay, so this is something you can find from the formal report from some papers. Now, so given that we have this fact, so I go to my own research, so I can share you something more interesting observations from the large language model. First of all, we talk about the limitation of current large language model. Although this is very expensive, it's very powerful, and people think that it may be capable of doing everything, but the fact is no. It's not a all around. It's not a super person. It's not a super computer. It still has some limitations. First of all, it is not very good at reasoning by rules. This is I give you an example. So basically, if you ask the question, say, I want to calculate the root of 2. This is the root of 2 here. So you can basically see the answer is correct. The root of 2 is 1.41421356, right? So this is correct. So then you can imagine saying, okay, giving this answer, I imagine that the system already learned the rules. I mean, how to calculate the square root, right? So you may think it this way, but the fact is not. If you ask the similar question, say, to calculate the root of 5,768, I mean, this is just a change a number and follow the same rule, and the system should give you the correct answer also. But the result is not correct, so there is something wrong in the result. It means what? It means sometimes you really don't know how the large language model learn the knowledge. I mean, some knowledge are learned in a very strange way. Probably the square root of 2 is learned by copying, by remembering the result. And then if you ask the question about the root of 5,000 or something, then the result is wrong, means that it does not know the rule by itself. Okay, so this is the first limitation. The second limitation is not very good at the long conversation. So if you're using the GPT-4 today, you can have some conversation. But if you keeping asking questions and let it go on and go on, then you find that after 10 conversations, so the GPT-4 already forget the early conversations. Already, he does not remember what you talk about. I mean, just 1 minute ago, and so this is called a forgetting. This is a conversation forgetting problem. And after 20 conversations, I mean, you see here, you see the last part. So after 20 conversations, the system says, okay, the conversation is too long. Please start a new one. So that means it cannot continue anymore. It's so exhaustive. So for the computer, all right. So that means the second limitation is that it's not very good at the long conversation. The third, of course, the third is the question problem is that it cannot answer very long questions. So if you input a book, I mean, you can ask questions normally. I mean, this is no problem for the GPT-4. But if you input a book, I mean, a fiction or academic paper, or whatever, a long book, then the system will say, okay, if I ask the system about the three-body problem, and by inputting a book with more than 30K tokens into the question, then the system will go wrong. I mean, it gives you irrelevant answers because it cannot understand all the tokens. And also the Llama 2 is an open source large language model, and this is give you even the wrong output. Say, model does not support a context size greater than the 4,000 tokens. Expect poor results. So this is the third limitation. And finally, I think we should let the system to know our visual world. I mean, currently we believe that language model is language, and the language cannot be connected very well to the visual world. So the large language model cannot understand the visual information pretty well. So if you input an image, a photo into the system and ask the system to describe this photo, say you see the result is rely on the imagination instead of the real photos input to the system, because this is some kind of poor connection between the language and the visual systems in the current machines. But it's changing now. We have the GPT-4V. This is already very powerful, but we still have found a large room to get a further improvement. So I give you a few interesting findings from my own research. So first work is to contribute to answering very, very long questions. So this is really our first work. So this work is called long LoRa and long alpaca. This figure tells you this is the alpaca, but it has a long neck, so it's called a long alpaca. Long alpaca is a model, so this is a new model. And this new model is very powerful. Why we call it powerful? Because I can give you some facts. First of all, there's an article just published just recently saying revolutionizing language models, long LoRa, unveiled as a game changer for efficient text sequence processing. So this is a comment from other experts in the AI area. And our code is already published on the GitHub, and it's top one, trained on Hugging Face and a paper with code. And this is already received about more than 180K views on Twitter for this work, and it is more than 1K GitHub stars in just 1 week. So I just want to show you how interesting this work is. And I know what this work is about. Here I give you a few examples, and these few examples are really interesting. I can show you. So I will slow down to let you know the exact the consequence about using such a model. So here first of all, below is a paper. Memorize the paper and answer my question after reading the paper. And this paper is shown on the right, and it contains more than 15,000 tokens. And then for other large language models, they cannot process this paper because this is too long. And if we want to further improve, then the question is based on the review guideline, because every conference has a review guideline. So please provide me some suggestions that would make the paper has more chance for acceptance. Okay, so the paper is so that means we ask the assistant to take the role as a reviewer to review the academic submission. So this is not achievable traditionally because the paper is too long. So here our system will give us some very useful suggestions. First of all, the first suggestion is to clarify the contributions and the novelty more precisely. So this is pretty good suggestion, and we know this is the problem when we submit the paper, and he clearly indicate that the system already found this problem. The second, provide more experimental details and results, and also it gives all the details following this sentence. Interesting. And the third suggestion is to discuss more potential applications and future directions. And this will increase the chance to get this paper accepted. And this is the 3 suggestions. And after this suggestion, we improve the paper and submit it to the conference, and it is accepted. So that means the system works. It's really useful. And this is just one example. Maybe this may not be very close related to some of you here, but I have more interesting examples. So this is analysis about economy, our economy. So below is economic outlook. Memorize the content and answer my questions of the book. And this book is Global Economic Prospects. It contains more than 42,000 tokens. And based on the material and your understanding, please predict the economy in the future. Okay, so that's really a tough task, right? So because the system has to read the whole book analysis and then predict what our global economy will change. And then the answer is here, is also listed here. I give you a few highlights. So based on the economic outlook from 2006 to 2023. Here are my predictions for the global economy in the future. First, growth will remain moderate and uneven across countries, with advanced economies like growing faster than emerging markets and developing economies. So this is the prediction made by the machine based on reading such analysis in past 15 years. So based on the 15 years economy change, and it gives the first prediction, so growth will remain moderate. Yes, from the end, this is already the end of 2023, and we noticed that this is true. The second, inflation will remain elevated, but start to come down from the high level seen in 2022 and 2023 as central banks continue to raise interest rates and commodity prices stabilize. And this is the second prediction. And from today's point of view, yes, it is still elevated, but it come down in terms of the speed, right? And the third one, the recovery from the COVID-19 pandemic will continue, but likely remain bumpy. So that means recovery will happen, but the process will be bumpy. And as new variants emerge periodically, and this is the prediction, third one. And the fourth one, downside risks will continue to outweigh outside potential. So that means there are still a lot of risks from the economy. And this economy, this kind of the risk going down economy is outweighed outside potential. And this is the trend prediction. And today you see, giving this year's the total performance of the economy market, we notice this is very correct. Then the structural reform will be needed to boost the productivity, supports inclusive growth, and facilitates transition to a green economy. And finally, central banks will gradually normalize monetary policies, but remain cautious and data dependent. Okay, so these are the few comments and prediction, and based on the economy. Okay, so that means after reading the book, you don't really need to read by your own. You just rely on the machine and input the book, and the book will be read by the systems successfully, and you will get all the essential information that the system can tell you. The third, another example, following by another example, this is the fiction, 西游记. Below is some section from the book, 西游记. Memorize the book contents and answer my question of the book. So Sun Wukong present undefeated strength when causing havoc in heaven, while he was later defeated by many monsters during the journey to the west. Why? Right. So this is a very interesting question. Say Sun Wukong was very powerful. I mean, when 大闹天宫, right? Then later on, when he go into the west, I mean, he become weaker and weaker. So what's the reason? So the system gives us some answers. Very interesting. He was still maturing. Okay, so when we get a material, we don't fight. So we argue with people, we don't fight, right? So this is the first reason, and it's very interesting. So when we get a material, so we sell them, we try to find other ways to solve problem instead of fighting, right? So this is the first point. The second point, he faced a stronger opponent. So when he was in heaven, so do some kind of rampage, then you can imagine. So everyone is trying to protect himself or herself, and then when he tried to face the monsters try to keep alive and keep a forever life. So this is totally two different situations. So that means he faced stronger opponents. We're very correct. And the third fact is that he faced the restrictions. All right. So when Sun Wukong was in heaven, there's no any restriction. But when he get on the road, I mean, then with the Buddha, with Tangsen, he has restrictions already. And also trickery. So because the monsters during the road are smarter than those 神仙in the heaven, because they have different ways to trick the Sun Wukong, right? So and also he need to help from others. So because today, so the Sun Wukong has some fellows. He has Tang Sen, he has other fellows, and he has to take care of. So that means he cannot put all his efforts to fight the monsters. Otherwise, the Tang Sen will disappear, right? So this is also this happens a lot during the role. So this is the analysis by this book, and assistants give you perfect answers. And so in summary, a combination of Sun Wukong's maturity and stronger components, restrictions on his power, deception, and lack of companion initially contributed to his defeat during the journey. But over time, he gained wisdom. He knows that he don't need to fight so hard. And experience and comrades that helped him to eventually overcome even the most formidable foes. Okay, so this is the answer. So basically, I give you for a few examples. So this is my science fiction about the three body. So this is my favorite book, science fiction. And so this question is why Ye Wenjie can contact aliens, and then why did he feel regretful in the end? I mean, anyone read this fiction, science fiction? I mean, this is really, really a good one. If you didn't, you should immediately go back to find one book, and this is an amazing book. And so the reason say ideally he wants to bring a superior alien to civilization to help fix humanity problem. Okay, so this is the first reason, so it's very correct. The second, for revenge. She wants to get revenge on humanity for persecuting her and killing her father. So because her father was killed by the Cultural Revolution, so because he has a kind of feeling of revenge in the beginning. So this is why he bring the aliens into the earth. So this is in the beginning, and then however, in the end, she seems to regret her actions because, first of all, he realized that potentially bring alien inventions, he had endangered all humanity. So this is not to help the human, it's to evacuate or eliminate all the humankind. So that means he feel regretful. And then as time passed and the society seemed to be improving with the advent of science and the rationality again, he found that humanity is not a problem that cannot be cured. Maybe human can cure by themselves. And after seeing humanity, the capacity of both the culture and the kindness during her time with the villagers, her views on humanity becomes more nuanced. Okay, so this is a few answers from that book. So basically, I give you this example showing you that we have a very useful, powerful, long context large model. This is open source already, so you can use it by your own, and you can use it as an interface to incorporate it into your research or work or whatever kind of things you need to do. I think I should stop here because my time is over, but I prepared a very long talk here. I have other talks I originally want to show you, but okay, I leave it to next chance. Okay, you will have a chance. Thank you.
Thank you so much. And please be seated. Don't worry, he is still here with us. And then later on, we will have panel discussion. After the panel, he is still here. You can ask him if you want to know more. So for the next keynote speaker is Professor Hu Wenmei. He is the Senior Distinguished Research Scientist and Senior Director of the Research at NVIDIA, the AMD Jerry Sanders Chair Professor Emeritus at the University of Illinois, Urbana-Champaign, and also ACM Fellow, IEEE Fellow. He's going to share with us about the topic accelerated computing and storage data access for in the age of AI. Even though he can't join us today, is going to share by video. Please enjoy.
Hello, everyone. It's an honor to be able to address this very prestigious audience. I'm going to be discussing our vision about the accelerated computing and storage data access for the age of AI. And I am a Senior Distinguished Research Scientist and Senior Director of Research at NVIDIA Corporation. Before I joined NVIDIA in 2020, I was a professor at the University of Illinois, Urbana-Champaign, and I was a faculty at the university for 33 years before I moved to NVIDIA. And this is a standard disclaimer. The views expressed in this the content belongs to me and my collaborators, meaning all my students and my collaboration researchers, but not NVIDIA, its affiliates or employees. So I'd like to start with the data-intensive AI access patterns that we're seeing in the field today. We're beginning to see a very important shift of AI models in the field. In the previous decade or so, started in 2012, the AI activities are focused or centered around models. These models are trained with massive amount of data, and the models are used to perform inference during the AI application use. However, in the past 5 years or so, we begin to realize, as a field, that these models have a lot of deficiencies. The most important deficiency is that these models are statistical summary of the data that are that are used in the training. However, during inference, because of the statistical nature, sometimes when the query come in, the model can have a phenomenon called hallucination. And this is because of the statistical nature of combining data, and sometimes the model will create information that is not really in individual data, but in some kind of strange statistical combination of the data, which does not reflect reality. Therefore, we have a very strong push in the field to incorporate real data and knowledge in the inference. And here on the left-hand side, I show that the query into a model such as ChatGPT-4, and that the model will be broken into two parts. One is the encoding, and one is a encoder, and one is a generator. So on the encoder side, the query will be encoded into embeddings, and the embeddings will be used by a retriever, which is a new component, into a knowledge base. And the knowledge base can be of a wide variety of nature. One is what we call the expert knowledge base. And the knowledge base could be in legal or different fields of the law, or medicine, and different fields of medicine, or it could also be general, meaning that the knowledge base could incorporate all the knowledge and material that a ordinary person going through kindergarten through the 12th grade would learn, and perhaps with what we call the general liberal college education. And such knowledge will be used as what we call the guardrail context into the inference process, and along with the query into the pre-trained large language model on the right-hand side, and before we derive the answer. With the real data and knowledge as guardrail, as the context, the inference can become much more stable, much more realistic, and hallucination. So this kind of retrieval will involve what we call this retrieval is called the retrieval augmented generation in the field, and the data can range easily from 10 terabytes to 1 petabyte. And the access pattern is to be able to select the relevant, what we call the rows and columns of the tabular format in the knowledge storage. And oftentimes we will need to use quite a bit of compute to be able to find the correct or the appropriate pieces of the knowledge from the database. Another important category of data access is the graph data access. In real world, things, all the entities and activities are all related to each other, and graphs are used to represent such relationship. And so, for example, when we look at any of the commercial transactions, the credit card, for example, each credit card transaction would involve banks, would involve consumers, would involve merchants, and it would also involve different types of intermediate settlement agency. And all these entities will form nodes in a graph, and these graphs can be extremely large. And then each node will have properties. So, for example, each consumer will have income, age, the previous purchase patterns and travel patterns, and so on. And such information is important during the transaction to be able to detect fraud in real time. And the fraud is $1 billion kind of damage to the business every year. And there's a very high value to be able to detect for fraud accurately without the false alarm. And the graphs are probably currently the best candidate for the next generation fraud detection. And such graphs can be easily varying from about 10 gigabytes to 100 terabytes. So the most important data access in this paradigm is the node features, and these node features are also stored in tabular format. So understanding how these access patterns work and how we can support this kind of access pattern on a very large, massive number and reasonable cost is going to be critical for the success of applying AI to the real applications in the coming decade. So I would like to show you a little bit about how the current data access work and how well we are supporting such access in the field today. And this is a measurement that we took when a GPU is used to accelerate data frame access. The data frames are the primary storage format for the data that I showed in the previous slide. And this is a simple query processing for New York taxi taxi data set. And so it's actually less less demanding than the previous two, but it's simpler so that it's easier to show the point. However, the observation applies directly to the data set for retrieval augmented generation and the graph and neural networks analytics. So when we access such a data set, we will be accessing pieces of data from the data frame storage. So I showed that in the picture, there are what we call the row groups, which are the pieces that we're accessing from the data frame. And the first row group is going to take more time because there are systems set up and so on. So we will skip that and look at the subsequent segments that we access, for example, row group 2. And when we look at the detailed timing of accessing the subsequent groups, we see that there is a very interesting breakdown of the time that are spent in the different activities for serving this request. 95% of the time for each row group in this GPU accelerated access to the data frame is spent in I/O service and memory management running on the CPU. And and only less than 5% of the time is actually spent on processing the data once the data arrives in the GPU. And this is, I showed the portion of the time that is actually spent on the GPU. And as we can see that this is a very unfortunate situation where the overhead to prepare the data for GPU execution accounts for the vast majority of the time in processing and accessing this data set. So what caused the problem that we're seeing in the previous slide is it can be illustrated with a simple cartoon illustration. So this is I took the previous slide and use a kind of a cartoon to explain what happened that in the past 2 decades that led to the observations that we're seeing today. About 20 years ago, if we execute the same queries or accesses, we will see something like the top portion of the graph. Each row group will be accessed by starting with operating system and file system service code. And so we will do a system call, and then the operating system and file system will execute, and then determine that it needs to go down to the driver to access the data. And then the yellow part, the orange part, is the storage devices such as disk. And today we're mostly moving into solid-state disks. The median access into the disk and the controller portion will account for the orange part. And then the data will come back, and there will be operating system and file system processing time to actually get the data into the compute device memory, and then eventually the application will process the data. So this process will repeat for the following row groups. So as we can see, the storage median access time, orange, and the application processing time, green, are big enough to hide most of the system, operating system and file system processing time. However, what happened in the past 20 years is that the applications have been drastically accelerated by devices like GPU. As you can see in the previous slide, the actual query processing is extremely fast, and a very short amount of time is needed to process that query on the GPU. And this is to the credit of so many engineers and product generations that led to the dramatic acceleration of the application portion. And also the storage devices actually have been improving behind the scenes in the past 20 years as we move from the old hard drive technology into the SSD, and then we moved from the old access protocol into the NVMe protocol, and now we have even faster protocol in the making. So the storage device and protocols have been drastically accelerated. However, the operating system and file system services running in the CPU kernel mode have not been accelerated significantly due to various technological constraints. Especially, one of the major factors is that the operating system running in the kernel mode cannot use many of the features, including vector processing and so on, in the modern processors. So today, if we look at the execution time, most of the time is actually spent in the operating system file system, and therefore we saw the real measurement in the previous slide. And in the near future, there will be further acceleration of storage devices. We already have seen the very nice improvements from Micron and Samsung and so on, and Phison, that the storage access time will be further reduced. And in the near future, we will have most of the processing time of data access, this data access and processing in the operating system and file system service. And this is a classic manifestation of the MDOS law. Right now, the percentage, there's a very significant percentage of time spent in the operating system and file system. Unfortunately, most of the industry efforts that we have been spending in the past 20 years and the next couple of years are in the application side and the storage side. Therefore, the further improvement that we can make by further accelerating applications and storage devices will be extremely limited, and that's exactly what is being stated in the MDOS law. So in industry, we already know that the operating system and file system is too slow to be able to keep up with the application needs and the storage devices, application acceleration. Therefore, currently, for GPUs at NVIDIA, for example, produced by NVIDIA, we have engineering efforts to avoid making storage accesses. So what we do is that is shown in this picture. So the storage contains all that data in the, let's say, in the data frame formats, but the storage data is opaque to applications except for memory map files. And the most prominent way of processing large amount of data is for the application to preload the contents from the file system and databases into the collected or what we call the pooled GPU memory, and shown on the left-hand side. And so once the data is loaded into the memory, then it can be accessed as data structures and code, so that we can operate and on the code using applications. So in this way, we only incur the operating system and file system service at the beginning of the application, and then we spend some time to transfer the data in the orange into the memory, and then we just keep cracking on cracking the cram on the data and keep processing the data in the memory and bypass all the operating system services and database services. So this is the reason. This is exactly the paradigm we're using for training large language models today. So as we move forward, we're going to begin to have a large number of applications that will be doing inference. And these inferences no longer have a very long training time. Training a large language model takes weeks of time on thousands of GPUs. And so with that kind of period of time, it's worth preloading the data into the memory and then just keep accessing data in the memory. However, for inference, each inference will last for only milliseconds. So preloading data into the memory would be much more costly and less effective as a model. So I'm showing a simple calculation. If we preload the data into the memory pool, it will be worthwhile if the initial preload cost plus all the access costs in the memory is much smaller than accessing the data from the storage. So the left-hand side is the cost for preloading and accessing in memory, and then the right-hand side is the access from the storage all the time. And however, in the inference application, in the AI, the new AI applications, the graph applications, and so on, we're seeing the access to the data is much more sparse than the training process. And therefore, it's actually not necessarily a good idea to preload all that data into the memory. And more importantly, the memory pool approach makes very expensive for massive data sets. So that very few applications can afford having thousands of GPUs pull together the memory just to be able to support these inferences. So there is an alternative approach in the field, and it's actually being used by people who cannot afford to pull together thousands of GPUs to process these massive data sets. It's called the memory map file access through page fault handling. So the way that this mechanism works is we start from the GPU on the lower left corner, where the GPU threads will access a virtual memory map data, and then because the data is in the storage, it's not going to be able to find the data in the memory, so it's going to trigger page fault, and then the page fault will actually go to the CPU, and the CPU will further process the page fault and bring that piece of data into the GPU. And this is a classic mechanism for people to access data that's beyond the memory size. However, for massive data sets, this approach can be extremely slow because the CPU software stack is not equipped to be able to process these page faults at the rate at which the data really needs to be accessed by the applications in the AI generation. So the CPU overhead would definitely limit the performance, and often GPU's PCIe bandwidth is not even close to be saturated, meaning that the hardware resources that will be able to bring the data into the GPU is underutilized. And this bandwidth is already orders of magnitude lower than the memory bandwidth of the GPU. Therefore, the whole approach will be just way too slow to be practical for real applications. So this is the reason why my research group at Illinois started to develop a new generation of data access service technology since 2015 at the University of Illinois. And so we built in collaboration with IBM and NVIDIA, we built a new software stack, and we enable the GPUs to be able to autonomously request data from the storage, bypassing the CPU software stack, and which is the major bottleneck. And then we leverage the GPU memory and optimize storage bandwidth utilization by having an extremely fast parallel memory management mechanism, which we call the software cache. And finally, we make the data set visible to the users through a array-like abstraction. So the application doesn't even need to worry about the data, but it just accesses a very, very large array. On the other, just like the memory map I/O, however, that access to a large array gets mapped in C++ into a piece of code that accesses the software cache and go through all the services in the user mode without going through the kernel. So with BAM, the GPU threads can directly request data where it is, be it in memory, someone else's memory, or storage. So I'm not going to go into the details, but for those who are more technically oriented, I'll just briefly talk about how it actually works in the GPU. For BAM, what happens in the application is that the data array access will be implemented as an offset calculation, and then do what we call the warp level coalescing to make sure that we capture situations where the threads access neighboring pieces of data. And then only one thread will need to represent all the other threads to access the cache if they access neighboring pieces of data. And if the data is hit in the access is hit in the cache, then the access is successful and the thread will continue to execute. If the data is missing from the cache, then the thread will go into a library mode and go into a library and prepare the I/O command and submit the command. And then the storage controller or services would do the service and come back with the data. And the original thread will wait for the completion and then clean up some of the data and then update the cache state and then continue execution. So if we look at the performance of this mechanism, the bottom red is the previous technology that was used for GPUs to access large storage data through the page fault handling mechanism. And this was published in ASPLUS 2013. And the upper end is the new BAM technology. As you can see, the effective bandwidth that we can have out of the accessing the data is is dramatically better than the page fault handling mechanism. And so this allows us to be able to access the massive amount of data at the speed that the applications really need. And so whenever there's a cache miss, we're able to submit all the requests to the storage devices, also at least 10 times faster than the previous technology. So how do we really achieve this? We use what we call the parallelism to tolerate storage access latency. As we know, the storage accesses have hundreds of microseconds or even millisecond latency. So most of the previous CPU-based software stacks could not tolerate such latency because they don't have enough parallelism. And the parallelism needed to tolerate latency is governed by what we call the Little's law, which was already originally designed to cover retail, calculating the retail space needed to create certain level of business. However, it applies exactly to this kind of storage access situation. So if we want to be able to deliver certain rate at data from the storage device at certain rate, such as the rate allowed by the PCIe or the interconnect the bandwidth. For example, for the Gen 4 technology, if we want to access data at 512 byte granularity, we can take the 25 gigabyte per second bandwidth of the PCIe and divide it by 512 byte delivery. And that gives us the rate at which we want to have the data delivered into the GPU, which is 50 million deliveries. And in order to be able to sustain 50 million deliveries for a Samsung data center level SSD today, we will need to be able to have 1,500 pending accesses at any moment in time during the time when we want to be able to sustain such delivery. In the previous software stacks, there's people were not able to get anywhere close to the 1,500 pending accesses from the application software through the system stack. However, through BAM, we're able to achieve this on a regular basis. So here's a simple evaluation of the technology. So we built a prototype system based on the Supermicro server box plus a H3 platform PCIe-based SSD box. And we can place the GPU either in the data storage box or in the server box, and then we can evaluate how fast the data can be accessed from the SSDs into the GPU. So we took the Amazon DGL library, that is the leading library for training and inferencing on the graph neural networks. We used the previous approach that is based on the page faulting mechanism, and then we created a new DGL data loader and incorporated the BAM mechanism into the DGL library, and this is called GIDS today, and it's being upstreamed into the DGL library, and this mechanism is for large data sets, the regular large graphs, this mechanism is probably only about 1.5 to 2 times faster. However, when it comes to the very large, in what we call the industry scale data sets, this mechanism can be 20, 30 times faster, or even more than 100 times faster compared to the previous technology. So let me just conclude by saying that why we really we are pushing so hard on the technology. If we're successful, we envision that in the next decade, we will enable pervasive use of knowledge base in future AI inferences. We will be able to support millisecond latency for retrieval augmented generation in AI query processing, and we can support these kind of inferences by with 100 times or more reduction in cost, and meaning the hardware and energy costs required to be able to execute these queries. Why is that important? The first one is what I mentioned in the opening. We need to guard against influence hallucination, and also we need to provide reference and source for proper explanation, verification, and credit. And this is so important in tomorrow's economy, where all the people who are contributing to the generated AI results to receive proper credit and probably even royalty from their work. And then we want to be able to make high quality AI inference affordable to the mass, so that we can make the AI advantage available to everyone except for only the most privileged, the corporations and so on. So there are many future directions that we will need to cover in order to make these kind of technology truly fruitful. One is we will enable many of our partners, such as Meta and Amazon and Microsoft, to be able to create new AI capabilities enabled by the fast access to the massive data sets. We are we're investigating accelerators for data access and movement. We're optimizing, specializing caching and buffer management. We have storage devices that supports finer grain gather, scatter efficiently. And we need to have improved I/O and network protocols for parallelism. We're building multi-GPU, multi-node support for scalability, and we're looking at GPU architecture innovations to even better support BAM with even higher performance and lower cost, and file system cloud infrastructure support to allow the user level services, parallel services, to be able to operate in more secure and efficient way, and the security isolation when accessing data using user-level services in general. And this concludes the talk, and thank you very much for listening to this presentation.
Thank you so much. Thank you for insightful sharing. To wrap up this session, may I now invite Professor Martin Wong, Professor Jia Jiaya, and Professor Wang Xiaogang to come to the stage to take a group photo together. May I invite three of you to come to the stage to have a photo. So get ready and then have a look to the center. 我们看一下中间的大会摄影师。One steps to the front, forward. Have a look to the center with your big smile. Continue to have a look to the center, and one more at the back. May I invite the video man? Maybe you can shift a little bit. Yeah, thank you so much. Do you need to capture the video? It's okay? Okay, thank you so much. Thank you. Once again, big hands to the three gentlemen on the stage. Thank you so much for insightful sharing. The upcoming section is about plant research for future agriculture. This session's convener is Professor Dong Xinnian. She is the Arts and Science Distinguished Professor of Biology, Duke University, investigator, Howard Hughes Medical Institute, member, U.S. National Academy of Sciences, member, the Science Committee of the Future Science Prize. Let's have a warm welcome to Professor Dong Xinnian.
Afternoon, distinguished guests, ladies and gentlemen. I'm Xinnian Dong, the organizer and the chair of this symposium on plant research for future agriculture. I'm so glad to see you here in Hong Kong. So as we all know, plant research plays an essential role in modern agriculture. Its development not only directly affects food security, but also have major impact on environmental protection and economic development. Only by improving crop varieties can we increase food production and crop resilience to the changing environment to feed the rapidly increasing world population. Only by reducing the reliance on chemical pesticides and fertilizers and their adverse effect on human and environmental health will we have a livable world in the future. Through this symposium, we, the Future Science Prize, hope to raise public awareness on the vital importance on plant research and celebrate the achievements of plant researchers in the Greater China area. So please allow me to introduce our distinguished three speakers for today's symposium. The first speaker is Dr. Sanwen Huang, President of Chinese Academy of Tropical Agricultural Sciences. He's also a professor of Agricultural Genomics Institute at Shenzhen, Chinese Academy of Agricultural Sciences. His speech will be focused on reinvention of potato. The second speaker will be Artao Wang from Center for Excellence in Molecular Plant Sciences, Chinese Academy of Sciences. He's going to deliver his speech under the title Sustainable Agriculture Fueled by Biological Nitrogen Fixation. The last but not the least speaker will be Cai Xiagao. She serves as a principal investigator at the Institute of Genetics and Developmental Biology of Chinese Academy of Sciences. So her speech titled today is Next Generation CRISPR Technology and Their Application in Crop Improvement. So let's welcome Dr. Huang to give the first speech.
And also, thank you, Professor Dong. Thank you so much. Please be seated. Now on stage is Professor Huang Sanwen, is the president of Chinese Academy of Tropical Agricultural Sciences, professor of Agricultural Genomics Institute at Shenzhen, Chinese Academy of Agricultural Sciences. Professor Dong also mentioned the topic he's going to present is the reinvention of potato. Let's pass the stage to Professor Huang.
Thank you. Thank you, Xinnian, to organize this symposium. And there's still a huge gap between population growth and food supply, and a lot of developing country, facing a serious food insecurity. But the availability of arable land reached a plateau, and the increase of food supply will rely more on technology, in particular plant breeding. You must think of China as second largest economy has secured food supply. But in fact, we import almost 100 million tons of soybean, which would occupy more than 760 million mu or 50 million hectares of arable land if grown in China. And we transport 100 million tons of grain from North China to South China, which equals the use of 100 billion cubic meter of water, more than 2 times of south to north water diversion project. This is a mega project in China to ship water from south to north. You know that North China, the water is insufficient. Let's look at the crop we grow. In fact, there are 2 types of crop. In the top 100 crop with largest acreage, 55 are sexually propagated by seeds, such as rice, maize, and wheat. And these crops are fast-breeding crops. And the other 45 are asexually propagated, clonal propagated, such as potato, cassava, and sweet potato. These are slow-breeding crops. Many of these slow-breeding crops are the staple food of developing countries. For example, cassava is the major staple food in Africa. The genetic potential of these slow-breeding crops are largely untapped. Potato is the number 3 staple food worldwide, feeding over 1 billion people in over 100 countries. It's quite nutritious and healthy food, yet it's clonally propagated with highly heterozygous genome. That means the genetics analysis and breeding is very slow. Here I wish to draw a comparison between car business and potato breeding. 120 years ago, Mercedes looks like this. Now it's very fancy. And 120 years ago, Receivable Bank is already a major variety in United States. It's still the number 1 variety in United States. In addition, the propagation index of potato is lower. About 10% of the total yield needs to be kept as seed potato for next year. The price for seed tuber is high. It takes $1,000 to $2,000 per hectare. Besides, the tubers often carry some disease and pathogens and pests. And our questions are, can we accelerate the breeding efficiency by changing the reproduction strategy of a crop? And can we make potato a more breeder-friendly and farmer-affordable crop? A few years ago, we initiated the U-Potato Plan, which is to transfer potato from a clonally propagated tetraploid crop. Tetraploid means they have 4 sets of chromosomes, into a seed diploid crop, reducing the breeding cycles from 10 to 12 years to 3 to 5 years, and increase the propagation coefficiency 1,000 times. Normally for 1 mu is a unit of acreage in China. That's 50 mu is 1 hectare. So for 1 mu, we need 200 kilo tubers as seeds. And now we only need 2 grams of seeds. And I happen to carry 2 grams of seeds in a tube. That's the need, the volume of seeds needed for 1 mu. 15 of this will grow 1 hectare. we will utilize heterosis, hybrid figure in potato. You know, heterosis was I think first recorded by our agronomist Jia Sixie many years ago. In 齐民要素is the China's first agricultural encyclopedia. Moors shows higher figure than the parents' donkey and the horse. And Charles Darwin also described the figure of hybrids by many experiments. Of course, we can learn from hybrid maize breeding. Between 1910 to 1970, the yield of maize increased by 8 times through hybrid breeding. Without hybrid maize, we would have no modern agriculture and no modern civilization. Yuan Longping and his team successfully increased rice yield by 50% using hybrid breeding, and he's my hero. What is science behind the rice heterosis? Han Bin and his team collected thousands of hybrid rice varieties and analyzed their genome. And they discovered that 16 core genetic genes contribute over 70% of heterosis. And this finding are of great significance in promoting design breeding of hybrid rice. For hybrid potato, the challenges are even bigger. It involves the transformation from tetraploid to diploid, meaning packaging genes from 4 sets of chromosomes into 2 sets of chromosomes, from asexual to sexual reproduction, from tuber to seeds. And its genome carries a lot of deleterious mutations and structural variations. Hybrid potato requires a deep understanding of the potato genome and the strategy of genome design. Here I would like to talk about our progress in 3 parts. First, we developed a deep understanding of the genome variation and evolution of potato. We decoded the hybrid genome in 2011, that's 1X, and we recently sequenced the 2X and the 4X genome of potato. Hybrid potato requires a broad genetic diversity, and we therefore developed a high-quality potato pangenome. Pan means a collection of genomes, diversity. Applying multi-omics and evolutionary analysis, we discovered the organ identity gene of tuber, IT1. If this gene is damaged, it won't have any tuber. And tuber is a new organ, newly evolved organ. It doesn't exist in the sister clade tomato and E. tuberosum. Potato and tomato are cousins in this sense. And we discovered IT1 received a signal from the leaf SP6A, move downward to the underground on the stem to make a tuber. Remember these 2 elements. I will talk about that later. And we discovered quite a mess in the evolution of potato. There's frequently interspecific crosses and gene flow. And this led us find a very interesting discovery, that the potato itself is a hybrid of tomato and the E. tuberosum. And the mitochondria genome told us tomato is the mother, E. tuberosum is the father. And the hybridization occurred around 9 million years ago, coincide with the repeat rapid uplift of the Andes mountain. And the hybridization brought SP6A from tomato and IT1 from E. tuberosum and create the tuber, which can survive in the high mountains, because in the high mountain, the temperature can be low, not good for flower. And the tuber is then a very useful alternative for survive the plants. And these events give rise to a major staple food crop. How lucky we are. And the hybridization events temporarily, we think, destroyed the stability of genome and thus lead to the birth of transposable element, TE. And we found the potato genome, in the potato genome, 90% of the structural variation are associated with TE because they have very active TE. It have a lot of structural variation, make the genome very, very, very dynamic and polymorphism. About 1.5 of the genome are found to be heterozygous SNPs, single nucleotide polymorphism, which is much higher than rice. Rice is about 0.5. And also surprisingly, about 13% of the potato genome are defined by structural variation. So added together, 15% of the genome are different between any two lines, between any two potato variety. And the inversion is one major type of structural variation and inhibit recombination. We therefore created an inversion map to avoid linkage drag. Linkage drag is a kind of not so good for breeding. When you want to use one gene, you always carry a lot of genes around that gene. So to make a hybrid, we need to develop two highly homozygous inbreeding lines as parents. And the major obstacle in inbreeding line development is deleterious mutation. Clonal propagation facilitates accumulation of large number of deleterious mutations, which can affect any traits. And this deleterious mutation often hide in heterozygous status. And because it's clonally propagated, it doesn't have any chance to become homozygous. You need to surfing to become homozygous. Normally, larger effects, deleterious mutation can be purged during surfing. However, when two deleterious mutations are tightly linked in repulsion phase, it is very difficult to eradicate them. The so-called Hill-Robertson interference, unless a crossing over between them was discovered. And that explains why some line cannot reach a high homozygosity. For example, this line has been self-crossed for 9 times. It still have 20% of the genome, more than 20% of the genome becoming heterozygous. Normally, when you self-cross a line for 6 times, it should reach the homozygosity of 99%. Even the fully homozygous inbreeding line, that's F1 and two inbreeding line besides it. Even they don't have larger effect deleterious mutation, it still carry a lot of mild effect deleterious mutation, which jointly result in negative fitness results, as can shown by frail growth, reduced fertility, and low yield. So it's imperative to identify all deleterious mutations and quantify their effects on fitness. However, the current algorithm, SIFT, can only predict non-synonymous deleterious mutation and cannot quantify their effects. We therefore apply a new method, genome evolutionary rate profiling curve, to quantify constraint size. But first, we need a deep phylogenetic tree. We developed a deep phylogenetic tree of 100 species in Solanaceae. Solanaceae is the family, botanical family of potato, tomato, so far. And we made alignment, whole gene alignment. And this phylogenetic tree covers 9 of the 13 clades of Solanaceae. And the total branch length is 4.05. That represents the number of substitution in ancestral allele at the neutral site. And this deep phylogeny ensured identification of evolutionary constraint sequence in the botanic family. It looks like a lens, evolutionary lens, to see in the potato genome during the 80 million years of evolution, which bases are very conserved, they don't change, which bases are quite evolved. So it's a differentiate, this lens differentiate the most constrained, most conserved from most changed. Using Gerber score of 2.75, we discovered 2.4% of the potato genome are constrained. A mutation on these constraint sites tend to be deleterious in potato. Out of this, 36% constraint sites are in non-coding region. And this data set combined with a genome, the variation map of 192 potato germplasm, we create a two-dimension map for potato. On this side is a genotype dimension. On the other side, vertical side, is the deleterious dimension. So on each base, you know which base is polymorphic, and you also know whether this base is deleterious or not. We found that 50% of deleterious mutation in non-coding region, and in the coding region, 1/3, totally 15%, are synonymous. We identified a deleterious allele, small FBA, which is control flower abortion, which contains a causal deleterious mutation in its promoter region. We cannot identify it using the previous algorithm. So prediction of deleterious mutation can help us on hybrid potato breeding. And we sequenced these 192 potato lines and adopt a formula to calculate the whole genome deleterious burden, that the total amount of deleterious mutation and times their effect. This led to a counterintuitive proposal. Normally we select the good-looking lines for breeding. Now we found the weaker lines carries less deleterious burden, which are in fact a better choice for developing inbreeding lines. So it's counterintuitive. And we incorporated this deleterious mutation map into genome prediction and increase the prediction accuracy for up to 45%. And when our paper released this year, and at the same week, there's a series of papers published in Science on the analysis of evolutionary constraints in the mammal genome, and also deleterious mutation for human disease study is quite similar to our study. With all this knowledge and tools, which we performed genome design of hybrid potato breeding. But we still have to overcome one of the obstacles, to break the self-incompatibility of potato. And this self-incompatibility is a two components system, sRNS in the stigma and F-box in the pollen, resembling the lock and the key. Weirdly, its own key cannot open the lock. So the strategy is that we either break the lock or we find a master key. We break the lock by genome editing of sRNAs and also find its natural mutants. On the other way, we found a gene. We find a gene of master key, the SLI gene, encoding a new F-box gene, F-box protein. And this discoveries led us to create self-compatible potato. With all these tools and information ready, we developed the first generation of a highly homozygous inbreeding line, up to 99 to 100%, using genome design, which involve 4 steps. First, selection of starting material of a high genome homozygosity. And second, genetic analysis of the segregation population for purging of deleterious mutations. And 3, breaking tied linkage of deleterious mutation to develop an elite line. And 4, crossing inbreeding lines with high genome complementarity to generate vigorous hybrids. And these 3 plants on the left are the mother plants, and those 3 are the father plants. They are not from tuber; they are from seeds. Looks quite similar. And then in the middle are the F1 hybrids, showing very strong heterosis. And this is our prototype hybrid U-potato1. It has already 50%, over 50% of the yield of commercial variety, showing a strong heterosis. Increased, they also have rather high dry matter content and high carotenoid rich content. Tastes very good. Of course, they also have some disadvantages. Remain in this first generation is prototype, requires continued genetic improvement. And we are developing a faster iterative breeding program for U-potato series. So this is the second generation will have new traits of a good tuber shape and a long dormancy period. And for U-potato 3, we have late blight resistance and long day condition, adapt to long day conditions. And for U-potato 4, we will have cytoplasmic male sterility. The potato doesn't need to have flower for the F1s. It can save the energy to make a bigger tuber. And for U-potato 5, we have high yield and stress tolerance. And each cycle will take about 2 or 3 years. So they really move to this fast track of potato breeding. This is a U-potato 1, where it looks like this. And the U-potato 4 is adding of 8 genome segments, and plus a cytoplasmic male sterility. These 9 components will make a U-potato 4. We have a time plan for 20 years in 4 sections, and we are now in the second 5 year. eventually, in this 20 years, we will make a full commercialization of this hybrid potato. And my team is now visiting Rwanda, planning small scale of field experiment there. And we also trained one of the PhD students there, and hope they will become a Rwanda potato breeder for hybrids. And our research received quite some positive comments. Professor Pete Morrow from University of Minnesota, he's a maize geneticist. He mentioned that it was one of the most ambitious and perhaps audacious projects. But it's quite a pleasure to discuss hybrid potato with Yuan Longping. He's the father of hybrid rice. That's half years before his passing away, and I hope I can show.
种子繁殖技术还可以解决那个马铃薯的这个病毒的问题。原来湖南省种马铃薯在内蒙去搞种子，好麻烦。马铃薯种子繁殖是革命性的技术。
I mentioned that hybrid seeds can solve the problem of virus, and also South China don't need to transport potato from North China as seed potato. The plan is a multi-group effort. I wish to thank all my colleagues, in particular Chen Zizhang from AGIS, Shang Yi from Yunnan, and Dong Songmeng from Nanjing. International Center of Potato contributed many germplasm. And I thank the Ministry of Agriculture, Ministry of Science and Technology, and SFC, Guangdong, and Shenzhen for funds. Thank you.
Thank you so much, Professor Huang, for interesting sharing. It's really insightful. Thank you, and please be seated. Our next keynote speaker is Professor Wang Ertao, investigator, Center for Excellence in Molecular Plant Sciences, Chinese Academy of Sciences, to share about sustainable agriculture fueled by biological nitrogen fixation. Let's welcome Professor Wang.
Hello, I'm Ertao Wang from CPAMS, Chinese Academy of Sciences. So today I'm going to talk about the agriculture fused by biological nitrogen fixation. To get it started, I would like to introduce our food. So we know we need carbohydrate, fats, protein, vitamins, and fiber, so every day. So protein tend to be particularly issue in our nutrient since the protein are unlike carbohydrate for most part. So the protein need we get enough protein so for human body for healthy. So we know that we want to protein-rich food every day. So something we are going to remember: nitrogen. Nitrogen is a critical element. So we need some protein-rich food, including some meat, milk. So of course, whether you eat meat or plant, all body. So the protein all body all come from plant. So we need plant every day. So where do this is the important question? Where do the plant nitrogen come from? So the nitrogen from plant nitrogen come from the soil mineral. So however, the fields grew over and over again, and the nitrogen soil will become depleted, which will not support plant growth. Will not support the plant to make protein for us. So how to overcome this? So at agriculture system, the overused field can be recovered by application of nitrogen fertilizer. So usually in form of ammonia. So we know that ammonia can be made from can be made from molecular nitrogen, which is the most abundant in nature. So in nature, but then we know that the 3 band of nitrogen is very stable. We need to break down these 3 band. This will cost a lot energy, use high temperature to convert molecular nitrogen to ammonia. So the ammonia was applicated into a soil. Plant can uptake ammonia to make protein. So, but this progress take a lot energy. So this is just to show you 1 or 2% of global energy was used to fix nitrogen to fertilizer plant. In addition, we know that excessive use of nitrogen fertilizer will lead to serious air pollution and water pollution and soil pollution. We know that in China, we cost around 1/3 of the nitrogen fertilizer. This indicating that a low efficiency in fertilizer uptake by our crop. So how to overcome this? How to reduce nitrogen fertilizer usement? So please let me introduce our root nodule symbiosis. Root nodule symbiosis is a mutual beneficial association between plant and rhizobia. In this symbiosis, plant can provide organic carbon from photosynthesis. Meanwhile, the rhizobia can fix nitrogen in nodule and provide ammonia to plant and promote plant growth. I would like to mention that most rhizobia can't fix nitrogen outside nodule. So the rhizobia need stay into nodule to fix nitrogen. So all this happened in nodule in room temperature, but no energy cost, only use the photosynthesis carbon. So just let me show you how important the legume in our agriculture system. Just recently, we found several fields. We did not apply any fertilizer, such as nitrogen, phosphate, and potassium. When we plant soybean in this field, we found that the soybean yield was not changed at all without nitrogen fertilizer application. That do indicate soybean achieve great yield without any fertilizer application. This field was last for 40 years, no any nitrogen fertilizer application. That do suggest the legume can deal with low nitrogen fixation. So we use modern technology and quantified the microbiome of the soybean root and found at least 2 key factors. One is some beneficial microbe cluster, and another is rhizobia. They function together to sustain soybean yield and low nitrogen fertilizer soil. So you can see the soybean can deal with low fertilizer condition and achieve great yield. So this is really important. So I just mentioned in 2022, around 150 million mu was used to grow soybean. So potentially every year we take 1/2 billion kilogram nitrogen put in 1/2 million kilogram nitrogen into the soil. So this kind of 1/2 billion kilogram can be totally removed or reduced. So I think the next policy or need to do something to reduce this kind of nitrogen fertilizer usement. So this is show you how powerful how important the legume-rhizobium symbiosis in our agriculture system. Since my lab has been working on macrosymbiosis for more than 10 years, we are interested in how do plants form symbiosis with rhizobia, where do legume-rhizobium symbiosis involved from. More and more evidence shows that there are some progress, some key gene in AM symbiosis was recruited by legume-rhizobium symbiosis lately, used for legume plant established symbiosis with rhizobia. Before this, I would like to introduce a little bit for AM symbiosis. AM symbiosis is really Asian symbiosis. You can see 80% of plants can form this symbiosis with macrolide fungi. So it was first described as by German botanist Frank. So in this symbiosis, the carbon flow to AM fungi, and inorganic nutrient move to plants, thereby providing a critical linkage between the plant and root and the soil. Just lately, the research found that phosphate is a major nutrient transferred from AM fungi to plant. Lately, my group together with other group found that the lipid are a major carbon source transferred from plant to arbustic macro fungi. But we know this by direct nutrient exchange was directly coordinated, regulated by host and environmental condition. So normally we see this nutrient exchange was regulated by phosphate condition. And the low phosphate condition, we normally see higher macrolide colonization. So just recently, we found that one MIP transcription factor we call PHR can associate with promoter of macrolide-related gene and promotes this gene expression. So we can see the low phosphate in soil can promote arbustic macrolide symbiosis. And the high phosphate condition, SPX can function as a phosphate sensor, directly inhibit PHR associated promoter of macrolide-related gene and inhibit this gene expression. So we see under high phosphate condition, low macrolide colonization. So under this, we can update the basic concept of arbustic macrolide symbiosis. In this mutual interaction, macrolide fungi can provide phosphate to plants. Meanwhile, plant can provide lipid as a major carbon source to arbustic macrolide fungi. This whole progress was controlled by SPX PHR module. So this PHR SPX module can make this symbiosis adapt to different environment conditions. So this is the basic concept of macrolide symbiosis, how plant establish symbiosis with macrolide fungi. But we know that in one key thing, this progress can be recruited by legume for rhizobia symbiosis. We know in legume-rhizobia symbiosis, root nodule is key, since rhizobia needs to stay in nodule to fix nitrogen. So next, we want to know how to plant form a nodule. So let me introduce a little bit of background. So in legume, the cortical cell can be dedifferentiated to form a nodule primordia. Lately form a nodule on legume root. But we know that in non-legume, the cortical cell cannot dedifferentiate to divide. So we think this progress, we think the cortical cell in legume and in non-legume could be very different. So based on this, we hypothesize that a unique property of legume root cortex cell may be fundamentally enable root nodule development. So based on this, we think some K gene maybe have some extended expression in this progress. Basically, we found one gene in this progress play important role in this progress, which is called SCAR. You can see here the legume SCAR gene in the middle. You can see the promoter of SCAR drive GFP expressed in endodermis and cortex cell. So the cortex cell lately can be developed for a nodule. But for non-legume AT SCAR, which only expressed in endodermis, so the two genes is very different, have different expression pattern in legume and non-legume. So next, we found that the SCAR and the SCAR-like double mutant show a defect in root nodule symbiosis. You can see here almost no nodule at a double mutant. So to suggest the SCAR gene is required for root nodule symbiosis, we know that SCAR gene is a K development gene. The mutant show short root, so the reduction of root nodule number could impact by root development. So we use specific cortex cell specific promoter to drive a SCAR dominant negative gene to reduce SCAR gene function in cortex cell specifically. So you can see the transgenic plant should reduce nodule formation. So this data indicate that cortex cell SCAR gene is required for root nodule development. Just to remember Philippe Benfei, who discovered 20 years ago for SCAR and SHR gene. SCAR gene is a grass transcription factor which expressed mainly in endodermis, just as I showed you before. This is in non-legume. Normally, SCAR gene interact with SHR to regulate root stem cell. You can see SHR gene expressed in steel and move into endodermis and interact with SCAR gene to regulate root stem cell. Just like in legume, we found that SHR gene mainly expressed in steel, like Arabidopsis, but surprisingly, we found the SCAR gene present in legume cortex cell. You just see here, this is a gas staining experiment, but Arabidopsis SCAR, a short root, not present in cortex cell. So that's indicating a short root gene can be expressed in steel, and the protein can move into cortex cell from the steel. So we also found that one region we call region 2 can determine a short root movement. Since in Arabidopsis 1, if we remove this region, we call the AT SCAR R2, the protein can move into cortex cell. That suggests that during evolution, legume plants lose region 2. This protein can have a bigger mobility, can move into cortex cell from steel. So of course, we use a cortex cell specific promoter try to knock down function of short root in cortex cell specifically. You can see here the root nodule formation was greatly significantly reduced in this transgenic plant. That suggests the protein SCAR in cortex cell is really important for root nodule development. So now we know that in legume, the stem cell program SHR gene are present in cortex cell, which will allow cortex cell with a competence for division. During resorbial infection, the symbiotic signal can active SCAR-HR gene and protein in cortex cell, which will lead cell division, finally form a nodule. But we know in non-legume arabidopsis, we see no SCAR-SHR, so no competence for division, so no nodule formation on a non-legume root. But I have no time to show the data. All data show that ectopic expression SCAR-SHR in non-legume could lead to cortex cell division. So that suggests that SCAR-SHR can be used to engineer cortex cell fate for nitrogen fixation in future. So this is how a nodule involved during resorbial evolution. But we know that resorbial symbiosis was formed 100 million years ago. And this progress was selected again and again during natural environment. But we know currently the soybean, the pea just grows in our agriculture system in farmland. So these two conditions is very different. So we just think we can further increase the efficiency of root nodule symbiosis. So the concept is I show here. This is wild type soybean. Normally we see the resorbial can fix nitrogen and feed plant. Meanwhile, the plant can translocate some carbon to resorbial to fix nitrogen. But this progress was selected during past 100 million. But in agriculture system, we think we can optimize the nodule formation and then slightly increase nodule number and increase nitrogen fixation ability to promote plant growth. Meanwhile, slightly increase carbon translocation to resorbial. Our collaborator, Yuefeng Guan, just generated a different kind of mutant. You can see here, this is wild type, HG-6, this is wild type. There's some mutant no nodule formation, some supernodulation mutant NAC1 show 600 nodule per plant. But you can see here, no nodule plant growth not so good, but high supernodulation plant, the plant grows smaller. But we do find some slightly increased root nodule symbiosis or root nodule number can promote plant growth. So we grow this plant in a field. You can see here, this is wild type, the plant grows yellow. So the transgenic plant, modification plant show dark green, which indicates the plant have more nitrogen. Also we just quantified the yield in 3 years, different place. We found that 10 to 30% of yield, soybean yield, increased in these two genetic modification plant. That suggests in agriculture system, we can rebalance nitrogen fixation and carbon exchange between plant and resorbial. So this is great. We show you how legume important for our agriculture system. Also, I show you how we can further improve legume resorbial symbiosis to promote legume product. But the problem, I told you, this is only happened in legume. But the biology nitrogen fixation is not is absent in non-legume. So everybody wants to engineer nitrogen fixation in non-legume. So in our field, 3 steps was proposed to engineer nitrogen fixing in non-legume. Step one, we try to engineer of associative with the nitrogen fixation between non-legume plant and the nitrogen fixing bacteria. The step two is engineer a key regulator of nodulation symbiosis in non-legume. In this step, we have successfully engineered rhizobia perception in non-legume rice. So you can see this is a calcium spiking trace. Normally, the rice can't respond to node factor well, but in transgenic plants, this plant can respond to node factor. So that suggests that we can engineer rhizobia perception in non-legume. As I mentioned before, use scarce HR, we can engineer non-legume corticel to divide. Probably in future, we can engineer a nodule at non-legume root to host the rhizobia. But a lot of people, a lot of labs work on this topic now. So step three is engineer nitrogenase in non-legume crop. But we know that it's really clear that engineer nitrogen fixation in non-legume, it will take long time. But it's already clear that all agriculture had been fused by nitrogen fixation in non-legume already, as I show you. But in future, I hope not so long, not so long. I hope agriculture can be fused by nitrogen fixation in non-legume. So I would like to stop here. Thanks to my lab members. Thanks for my collaborators. Also, thanks for your attention.
We also thank you for your insightful sharing. Thank you so much. Please be seated. Thank you very much. Next, we are thrilled to have Professor Gao Caixia, Principal Investigator, Institute of Genetics and Developmental Biology, Chinese Academy of Sciences, to share about next-generation CRISPR technologies and their applications in crop improvement. Let's welcome Professor Gao.
Okay, thank you. Hello, everyone. So first, I would like to thank Professor Xinyan Dong for inviting me and give me a chance to speak at this Future Science Symposium. Today, I will present a talk on the advancement of precision aging technologies and their application in crop improvement. So as everyone here knows, that DNA is a building block to all of life. So changes in DNA may affect the resulting protein, which change the physical property of living cell. So, however, during the process of DNA replication, some mistakes can cause some extremely devastating diseases. As you can see here, some genetic diseases are caused just by a few letter differences. DNA changes or DNA sequence changes are sometimes required in or designed in many applications. Here, example, in crop breeding, breeders relies on these genetic changes that accumulate over years to breed or to create a new and desired variety. So here you can see the modern varieties of corn and banana. They look vastly different from their ancestral looks. So the grand question to the field of genome editing is how we can precisely or accurately to edit a gene of interest, among a vast genome. So here, human genome is 3 billion bases long, while this wheat genome is 5 times of that. So then it's very critical to answer the question how to precisely to find this target site without affecting the other locations. So the field of genome editing is not new. Over the past 30 years, we have seen many developed tools that can edit DNA sequences. So here, like meganucleases, zinc finger nucleases, and the talon, they are like three of the notable examples. So however, they all rely on this direct or strict protein DNA bonding interactions to target a sequence of DNA. So to target a new sequence of DNA, one would have to extensively engineer and optimize this protein complex. So CRISPR technologies have advanced the development of the field of genome editing as its first demonstration as a gene editing tool since in 2012. So then the CRISPR-Cas9 systems are like fundamentally comprised of a Cas9 nucleus directed to the target site by a single guide RNA molecular. So this single guide RNA molecular serves as a GPS function to direct this nuclear protein to the target site. A simple, very simple sequence changes in this guide RNA will enable redirecting this nuclear protein to a new target of site. It's because of that, then this technology was awarded Nobel Prize in Chemistry in 2012 to Jennifer Doudna and Emanuela Charpentier. So we need to, when we look at what CRISPR systems do, we found on the right, we found that the CRISPR first generate a double-strand break. So upon recognition of the double-strand break, the cell rapidly attempts to repair the break. Although one can introduce a template to direct a more precise outcome, this occurs like rarely in most cells. So then on the other hand, so this repair at the double-strand break will undergo a process called the non-homologous adjoining, which results in this formation of some random DNA or small DNA insertions or deletions, which ultimately knock out the gene. So then the first generation of CRISPR-Cas9 are very good or great at performing gene knockout. So gene knockout are very important also in plant breeding. So the normal or the current molecular method to breed for disease resistance rely on a resistant gene, R gene. So R gene mediated resistance is R gene is very often race specific. So then pathogens can easily overcome this resistance by introducing some mutations in fungus. And often we need to, or people need to introduce R gene from one variety to another, which through this transgenesis or crossbreeding method, which takes a lot of time. So alternatively, susceptibility gene, S gene, is endogenous gene in plant cells that pathogen leverages to infect plant cell. So disturbing or engineering S gene enables this broad spectrum and durable resistance. So Podomino disease is a major disease affecting wheat yield worldwide. And the Podomino disease is also one of the top 3 wheat diseases in China. So currently, people use chemical fungicide to kill this Podomino fungus. However, this method is not sustainable and it's harmful for farmers and the consumers. The MLO gene is a very well-known S gene, and this gene is very conserved. You can see in barley or Arabidopsis, tomato, and pea. When knocking out this gene in these 3 plant species, so the plant showed resistance to Podomino. So in wheat, there are 3 copies of ML gene across this 4 or 3 genome of wheat. So in 2014, my group, in collaboration with the others, used Thailand technology to knock out 3 copies of this gene, and we demonstrate that this triple mutant showed robust resistance to Podomino disease. Okay, one slide missed. But anyway, so when we grew this triple mutant in the field, we noticed that the triple mutant showed some decreased yield while producing additional ML mutant. We identified an interesting mutant called R32. R32 showed a very normal plant height and will enhance the yield. So since 2014, we used nearly 8 years to uncover this, the biological basis behind this phenotype. Oh, sorry. So here, we found in R32, there existed a 304 kilobase pair large deletion. So the deletion is bordered by MLO-B1 and also by a newly identified gene or homolog of MLO, we call it MLOX. Through comparative studies, we found a gene was upregulated just upstream of this deletion region. The gene is TMT3B. So this gene did not express in this wild-type plant. So this gene is tonoplast monosaccharide transporter. So previous study showed that all expressing this gene in Arabidopsis increased green yield. So then through many years study, we found that in wild-type plant, the transcription of this TMT3B was depressed by this, the presence of this depressive histone mark H3K27 trimethylation and also an inhibitory chromatin loop. While in R32, this large deletion abolishes this epigenetic depression, thus resulting in the transcription increase of TMT3B. So in summary, R32 is comprised of 4 simultaneous DNA double-strand breaks, which result in 3 genes knockout and 1 gene upregulation, yielding this decreased disease-resistant and high-yielding wheat. So we certainly want to introduce this R32 in more wheat germplasms. So therefore, we use genome editing. We introduce the I think something wrong with my slide, but okay. Okay. So we introduced this genotype through genome editing, and we used this CRISPR DNA or RNP, this protein complex directly with the 2 guide RNAs, and we were able to regenerate this transgene-free and edited plants in 2 to 3 months. So then, in conclusion, we developed a new method which uses genome editing to breed for this wheat plants with robust, durable, resistant, and enhanced crop yield. So although powerful, it's gene editing powerful in itself, but still it's very much limited by the types of traits they can directly affect. And the single nucleotide polymorphisms are the most prevalent in treating genetic diseases and being associated with the plant traits. So here, from this figure, you can see nearly 50% of the human genetic variants associated with disease is caused by a single nucleotide chains. And also more than 40,000 DNA SNPs are related to 34 traits in rice. So then we need to develop some tool which can edit small DNA changes precisely and efficiently. So base editors, originally developed by WS Group, are the technology that can change one base at one time. So the cytosine base editor and the adenosine base editor are the two primary base editors. So they undergo this either cytosine deamination reaction or adenosine deamination reaction to yield uracil or inosine intermediate and ultimately convert to thymine or guanine. So my group first generated this first plant-based editors by optimizing this cytosine base editor, and we found this base editor is limited in narrow deamination window and also some certain contexts, and with overall lower DNA editing efficiency. So we analyzed or we screened many other different deaminases and found that human ApoBec3B or 3A is when we use this, the use of this human ApoBec3B can greatly enhance this editing efficiency and across different plant species. And our A3A PBE performed about like 11-fold better in potato and 13-fold better in rice and wheat. And the other groups continue to demonstrate that this A3A base editor worked better than the first generation. However, editing was also limited in soybean. So to develop more base editors, so we developed a method on using this massively parallel AI assistant structure prediction and this similarity alignment to identify proteins with some designed property. So when we applied this method in the family of this deaminase of proteins, we found that the structure-based clustering of protein, the method are more clear and concise than the traditional sequence-based clustering method. So through a high throughput deamination profiling assay, we found this newly discovered editor deaminases showed some very unique property when used as base editor. So here you can see they have very different editing efficiency and a very different, what's that called, motif preferences. So also we were excited to find that some base editors showed very low off-target activity. So through this orthogonal R-loop assay that my group and the other developed, we found that like SDD6 showed the best on to off target ratio. So we further want to engineer all these base editors. So we found that we noticed that this, in addition to this co-domain of deaminase, there are some additional loops, which didn't seem to be related with the co-activity. So with the help of AI, structure prediction again, we truncated this base editor, deaminase, and we were very excited to find that the truncated version had similar or even better editing efficiency compared to the old one. So we're very excited to say that we could use, using this truncated version, actually is a newly created protein for this base editing. So then we applied this newly discovered base editor in soybean, and we used the mini SDD7. And you can see this new base editor increased the efficiency much more than the old version. And then we also delivered the new base editor and also the old version to generate this or to regenerate this soybean transgenic plant. So across all, or like 4 parallel experiments, we could we see the old version A3A did not yield any edited plant, while this newly discovered base editor really gave or produced a lot edited plants with when we target the herbicide gene. So in addition to using base editor to make base change or very specific variant, we were also one of the first group to use this base editor as great mutagenesis editors. So we fused cytosine and adenosine to a fusion protein in order to make this C2T and A2G at one target. So we wanted to use this STEM system to explore new biology. So here's an example. So we use STEM to explore endogenous mutations in order to identify some new herbicide-resistant target site. So we target the ACC gene. ACC is a key enzyme in lipid biosynthesis, and its CT domain is its CT domain is a target of herbicide. So we focused this CT domain and designed 200 sgRNAs, and then we could see we transformed them into agrobacterial and group agrobacterial, and delivered them into rice chyli to yield a library of seedling. Upon this herbicide spring, we identified some variant. So when genotyping this edited plants, we found 92% of the sgRNA has been successfully introduced into the plants, and yielding or results in 209 of 400 amino acids have been changed to new identity. Something wrong again. Okay, so this, then I'm trying to say there are, you have to imagine this slide. So there are 2 groups. We identified 2 different mutations. One mutation has been repopulated previously, and the other one is a novel target we found, which herbicide resistant. I don't know what happened here. So then, base editing, we just mentioned, is super rare at make one base change. However, it is limited by the base change types. So therefore, in 19 in 2019, David Liu's group developed this or pioneered the development of this prime editing that enables the creation of 12 base changes or base substitutions. And also, the system enables the precise small DNA insertions and deletions. So when we first generate this prime editor system in plant, we found that the efficiency of prime editors varied widely across target loci and also different cell types. And the efficiency is strongly affected by the design of the pegged RNA. So to maximize the utility of this plant prime editing, we made some improvement. And firstly, we screened many pegRNA designs, and we found designing primer binding site with a melting temperature of 30 degrees leads to optimal performance in rest. And the different temperature or different melting temperature work best for different plant species. And we were also one of the first, or we were the first, to demonstrate that using dual pegRNA in trans encoding the same edits further enhance PE efficiency. So when we combined these two strategies, we found the optimized dual pegRNA boosted the PE efficiency from 2.9-fold to 17.4-fold. So we further optimized this system by changing, the next we engineered this Cas9 nickase transposes fusion protein by truncating this RNase H and also insertion an RNA viral nucleocapsid to generate this EPPE system. And from this figure, you can see this EPP system enhanced the prime editing on average 5.8-fold in plants. So using EPPB system, we were able, we generated a RAS mutant endowed high level of resistance to a broad spectrum of herbicide. So finally, we would like to, or we wonder if we could use this precise genome editing to find or to turn protein expression levels. So here we see in about like 50% of eukaryotic genes, they are regions. There are regions called upstream open reading frame. And this upstream open reading frame, URF, affects the translation of this primary open reading frame, which overexpress the target gene. So we wonder, or we hypothesize, by making change on this URF, we may enable this gene overexpression. So vitamin C is this valuable nutrients in lettuce. So GGP1 encodes a vitamin C biosynthesis enzyme in lettuce. So then indeed, some small edits in this URF of GGP1 enabled increased vitamin C level in lettuce leaves. So further, this BZIP enables sucrose-induced expression of translation in strawberry, which affect the overall sweetness in strawberry. So we introduced, or we generated a variety of allele by using a base editor. And here you can see this edited strawberry inhibited increased sugar in, So then indeed, by precisely changing or modifying URF, we are able to upregulate gene expression. So then we wonder if we could downregulate the gene expression by modifying URF. So we first attempt to use base and prime editing to generate de novo URF while creating upstream start codon ATG in hopes to slowing down this protein expression. And then we further hypothesized that if we could enhance this inhibitory activity by extending endogenous URF while mutating existing stop codon. So then that's a target gene, and we generated a variety of this allele by making some changes in this 5' UTR of RAS DLT, and the engineered URF reduced this lack activity progressively. And very excitingly, we found the plant heights and the telomere numbers of the mutants decreased progressively, consistent with the corresponding reduction in RAS DLT level seen in the transient report system. So with all this small DNA editing method on hand, we're wondering if we could work on a method which can insert a large DNA fragment. So then we designed or we combined prime editing and the recombinant system to generate prime root. So in prime root, we could insert these recombinant sites in which them serve as a substrate for recombinase. And here is an example. Then we inserted this 4.9 kb DNA sequence, which encoding this pig MR, which confers RAS resistant to RAS blast disease. And here is this demonstrate that when we successfully inserted the gene at the genomic harbor site, we see this resistant phenotype. So I hope the method demonstrated above illustrates the breadth of this genome editing technologies developed over the past 10 years, and also some examples. And I'm excited to see where this genome editing will advance, and I hope to see more commercial products enter to market. Okay, so then finally, I would like to thank the people in my lab who work very hard for all the work I saw today, and I'd like to thank our great collaborators and also these funding agencies. Thank you for your listening.
Thank you so much, Pascal. Please remain on stage. Now we're going to have a panel discussion. Today is almost the end of the day. We are going to have a panel discussions to wrap up today's event. And then actually, as Professor Lo also mentioned, for this week, we have so many stunning programs. Tomorrow, we are going to have the symposium as well. And then later on, we have the Asian Young Scientist Fellowship Annual Conference. It will also cover the sharing about the life science, physical science, mathematics, and computer science. And also, we have the Future Science Prize narrates dialogue with the youth. And finally, of course, very important, the award ceremony. So we are so looking forward to it. And now we are going to have the panel discussion. May I invite our moderator, Professor Dong Xinlian, and also our panelists, including Professor Gao Chaixia, Professor Huang Shanwen, and also Professor Wang Ertao. Let's welcome them. And then before the panel discussion, let's have a photo first. May I invite all the guest speakers proceed to in front of the stage at the photo first. 我们先拍一张合影好吗？ So let's have a look to the center to have the best photo. One more to go. And thank you so much. So now I pass the time to Professor Dong. Big hands, please.
All right. So now we're going to kind of do a Q&A session. So I prepared 3 questions, and I hope that my speakers will give their best shot at answers to these questions, okay? So we're going in this direction. Is that okay? All right, so the first one is, what is the most fascinating thing about plants that you discovered through your study of plants? Yeah.
What's the question?
Okay. So what is the most fascinating things about plants that you discovered through your study?
Okay, that's a good question. I think it's very exciting to see this the genetic diversity among these different plant species. For example, when people work with genome genetics, then they focus on one genome, human. And then when we work with the plants, then the plants even, the genomes are very different between different species, and even in same species, and they have very different variety. So therefore, I think it's very, very exciting. And also, I think sometimes they can look very similar, like rice and wheat. They have very similar height, but then if you think about the genome, the wheat genome is 40 times larger or bigger than the rice genome. So that's very, very different. And I'm thinking, but otherwise, this sometimes I think it's also a good thing if, although they are different, but some pathways are very identical. So then, because I work with genome editing, so I really can borrow some information from the other crop of the other plant species and use this knowledge to make some modification. So I think that's something good.
All right.
Thank you.
Yeah, when I studied potato, I found how fluid, dynamic, and plastic of
Yes,
plant genome
yeah,
could
I
be.
agree.
Tomato, between any 2 lines of tomato, they are quite similar, very conserved. Between any 2 potato genome, the difference could be huge. So if you don't tell me it's all from potato, just give you 2 sequences, you must think they are from distantly related. It can up to 15 to 20% of difference. And you know that between human and chimpanzee, there are only 2% of difference. 2% of genome are different. So this is quite give me an impression how flexible of plant genome could be.
Hi, Tom.
Okay, I think one most fascinating related to my research is how plants involve to interaction a wide range of microbes.
Yeah.
Since in 2015, we found that one gene, we call the SERC1, can directly regulate plant defense or plant symbiosis. So I think this open one window we can study how plants distinguish friends or foes. So at that time, it's quite exciting during the past several years, since almost every month or every year, the hypothesis or the concept related to this topic is changed very often. So probably this year we have a concept of this, but next year will be changed. So I think it's very exciting. It's a very funny thing for me. So yeah.
Yeah. So to me, through my study of plants, since I was trained in microbiology, so I never really formally trained in plant biology. But what fascinates me the most is the plasticity and resilience of plants. Plasticity means that you can have the same plant species and plant it is so rely on its development is so rely on the environment. So all of you have seen bonsai, right? Penzai, right? So you can have a big tree in outside, but if you put it in a pot, it can be a bonsai, right? So that's the plasticity of the plant. So its development is highly dependent on the environmental conditions. At the same time, it's so resilient. So some of us have seen very old trees, right? So they can live for hundreds of years or even over 1,000 years, but they still keep their stem cells, right? So they still have so they're exposed to radiation every day, and then for so many years, but then you still have the same plant. So, and also aging, right? So you talk about aging in animals, but then if you think about aging in plants, it's hard to define, right? So you may have a very old tree, but then something new will come out, like a new branch will come out. So how do you count its age, right? So I found that really, as a biologist, so fascinating. Okay, so the second question is, what is the biggest obstacle in further improving crop yield and resilience?
Yeah, that's a good question. So I think over the past 10 years, then biotechnology research has developed many tools, such as genome editing. But then we hear tools to modify genome, but the question remains where to edit, what gene we need to work with. So the question is if we hear enough biology. So therefore, I think with all these fancy or modern or this high throughput technologies, we are able to explore new biology efficiently or faster. So I think that's very, yeah.
Okay, so yes.
Yes, to me, first we have to identify discover the genetic basis of these complex traits. Yield and resilience are both controlled by many genes. That's the first question to be answered. It's not easy. And second is that if we already found those genes, how to arrange them in a genome through breeding is also very difficult. So each gene not only will incorporate as one gene, they will bring the neighborhood together during breeding. How to minimize and precisely transport one gene. Of course, gene editing is one process, can be done. But still, how to simultaneously manage so many genes is very difficult. So still a lot of improvement in technology has to be done.
Okay, I think the big challenge for our agriculture is uncertainty or unpredictable. Since in the last 30 years, the crop genetics or crop genetics always study the yield and the pathogen resistance gene. So since this trait was selected again and again during plant domestication. But you know, now our agriculture system faces to climate change. So the gene can adapt to climate change. Sorry, we don't know which kind of gene can be used to adapt to climate change. Additionally, this kind of gene might not be in current cultivar. So we need new resources or new gene and to deal with the climate change. So I think that a big change is uncertain. We don't know which gene or which kind of gene we need. So that's what I think the problem. Yeah.
Yeah, I agree with Sartao because, for gene editing, right? So you have to have the gene there to edit, right? So if resilience or even increase yield even higher, then you may need to introduce something new. And that I think is, we may have to consider transgenic. So because to bring in new genes in order for to overcome the current challenge and the changing environment. Yeah. So I don't know whether you agree with this or not, because we do CRISPR-Cas9 to avoid the technology that people worry about, the transgenic technology. But I think we still need to be.
But I think another problem is, but we don't know how to deal with the climate change. But we don't know, since in agriculture system, this trait was not selected at all during plant domestication. So we need to find a method to explore which kind of gene can function in this progress.
Right. It's never been selected. Yes. Yeah. All right. So the third one is, what are the currently used methods to improve crop performance? So I think that's a simple question.
Okay.
But then, yeah.
Yeah, so I think we have seen this, we just mentioned this GMO technology. Actually, I think in particular GMO technology, which can allow us to create this new transgenic plants. I think all these transgenic plants really help a lot with yield increase. We have seen this transgenic corn or transgenic soybean. But then they also, we could also say this genome editing really accelerates this plant breeding. So I can give you a very simple example. Like I just mentioned, this polymutal disease. It's not only disease for wheat, it's also for barley. But barley is diploid. And in 30 or 40 years ago, breeders found a mutant of barley, and they could, then this natural mutation, then breeders introgress this resistance through traditional breeding to all these modern barley varieties. You don't see any disease, polymutal disease in barley any longer since last 40 years. But if you look at this wheat, the wheat has 3 genomes. So simultaneously knock out 1 gene in nature is a very, very big challenge. But I just mentioned with the new technology, we could do that with gene editing, and easily in 2-3 months, we produce that. So I think this genome editing, both GMO and genome editing, will greatly accelerate our plant breeding.
Yeah, I think that during the domestication of the crop we grow today, only a small section of polymorphism and diversity are passed away through this domestication. Still larger section of polymorphism diversity not being studied or used. These are readily to be explored for to improve the current variety. I think at least one trace, and for all the wild plants are adapt to soil with no fertilizer, and to improve the performance on the lower input of fertilizer, we could use those genes.
So I just follow someone's comment. I think that in the last 50 years, the most successful method to increase crops performance is use fertilizer. So we add a lot of fertilizer in our agricultural system, but at the same time this causes severe pollution. So such as or air or water or soil. So I think in the next stage we need to reduce fertilizer input, or even we need to stop doing it. But how to do it? I think that it could be much more rely on some beneficial microbes, also increase plant nutrient uptake efficiency. But from my side, I think, as I mentioned in my talk, since in our agriculture system, at least the legume rhizobium symbiosis should be much more adapted in our agriculture system. So in this system, we can reduce or even no nitrogen fertilizer applied. So this can clearly reduce nitrogen fertilizer usage. In other side, the micro-related symbiosis, which can help plants get phosphate and nitrogen. So this symbiosis really abroad happened in different plant species, such as wheat, maize, or rice. So we could find some new variation gene can increase this crop interaction with the macrofungi and can further reduce phosphate and nitrogen and input. So that's I thought. Yeah.
Very good. So we have about 8 minutes to answer questions from people who's here to attend this seminar. And I was told that there are quite a few plant labs in Hong Kong, but compared to the number of labs studying plants in mainland, I think there's a smaller number. So please use this good opportunity to ask your questions. Yes, please.
First of all, very happy to hear such a wonderful topics from you guys. And after hearing this, maybe one sentence coming to my mind, which is, I think the things you guys are doing is small things make greater. Because I can feel like all of the plants we can see every day in our lives, but the very small things maybe you do in the genome make that very big changes. So after hearing two topics in this afternoon, one is the computer science and one is the maybe the things you guys are doing. So I'm wondering and very curious about, do you think the computer science or AI can really help to push your succeed in the maybe the research or the process of the things you're doing? So that's the things I really want to know from your topic or the respects. Yeah, thank you.
Okay, thank you for your comments. I think this come back to the second question. And I think this, in order to explore new biology, so we need to combine all these new technologies. And I didn't mention an AI. Actually, I should mention that. I think AI help us a lot, at least in my lab. We use AI or AlphaFold to predict this protein structure. And by this way, we really identified a lot new deaminases. So I think with AI's help, we could get new data and we gain some new insights into some new biology. So, yeah.
And I think AI is, thank you for your question. AI will be important to cross-learning, that we have so many plants. And we can learn from each other because all plants share a common ancestor. We could, and all the literatures, all the paper published, they are isolated islands, and we can link them together. And there are there are many ways of using AI, and I think it's very compatible with genomics and bioinformatics we studied.
Currently, I try to hear some AI people in my life. Since we think in symbiosis, there are lots of genes, thousands of genes there. We know already that could be involved. So if we have in AI, we can predict the interaction, predict protein-protein interaction between 2 proteins or 3 proteins or among 5 proteins. Then we can see at plasma membrane a big complex there, and the transcription factor complex, something rare that could be find a lot of new component which we will know we don't know before. Then we can use reverse genetics to find a new component. That's what I think the AI could help me a lot, at least. Yeah.
So to me, we recently had an experience with this because we've been studying a RNA hairpin structure we discovered that regulates translation. But the sequence of the hairpin is not conserved. So then you have to describe this structure, right? So how do you describe this? There's no sequence conservation. So we had to collaborate with Cliff Zhang's lab in Tsinghua University to analyze our translational data and RNA folding data. So we end up then describe the hairpin by the length of the hairpin, the number of hairpins, and also the folding energy. So I think this type of use of AI for data analysis or describing specific phenomenon, I think we will start to use AI more and more frequently. So it's not just for plant research, I think for all biological questions. Yeah. Yes, there's one. Please. Did we answer your question? Good? Yeah, all right. Yes, please.
Hello. Thank you very much for all your wonderful presentations. I have a question about global warming. Has the weather pattern changed now that we are getting warmer and warmer, been affecting all the agriculture? And what do you think it will happen in the future if the temperatures keeps going up?
Yeah,
the genes or DNA, would that be affected?
Yeah, that's very, very good and a very big question. And I think, come back to Simon's answer, actually, I think in the future, because currently we cannot solve the problem, because if you look at for the past several years, our breeders aimed at high yield rather than the other things. So therefore, our genetic diversity has been decreased dramatically. So therefore, we need in the future, or currently, we need to start to think about explore all these wild plants, which are very resistant, they have very good thing without high yield. So if we know a lot about yield, so we could make this, we could increase yield on the base of this wild plants. So I think it could be a very big source we need to take advantage in the future. Of course, we need more technologies to make more or new trees that can meet the climate change. But I think there are two things. One is we need to have enough resource. And secondly, we need to have technology. We can also artificially make these trees.
Two parts. First, we have to get ready for climate change in plant breeding to develop a new variety adapt to high temperature or climate change. Secondly, is that we should be more positively working for solve the problem. Number one is to reduce the carbon footprinting of agriculture. Now we use a lot of fertilizer and a lot of water, and we should reduce that. That can be done by plant breeding and other measures. And the second is that we didn't apply our technology on others, not crop, trees, grasses. We should apply all the technology on those plants and grow them more, which will we capture CO2 and to really to stop this bad direction. And that was not touched so far yet on grass and trees. And we should apply all technology on that part to be more positive and more active on really curb the climate change.
I just share one sample how to deal with the high temperature. In rice, Hong Xuan Lin, just in our institute, Professor Hong Xuan Lin, he collects some rice from Africa. So there are a lot high temperature resistance there, so we can clone this gene and introgrowth this gene into all variety in mainland then, and this new variety will be cultivar will resistant to high temperature. This is just one sample, how we can deal with this kind of issue.
I think we're running out of time. Thank you very much for coming to give your beautiful presentations, and thank you for joining us and to spend the past 2 hours with us. So if you have more questions, please come over, and then we will stay around to answer your questions in person. Thank you very much.
Thank you so much, and please be seated. Thank you. So now is the finale for today's symposium. Once again, thank you so much for joining the Future Science Prize Week and the 2023 Future Science Prize Symposium. I hope you enjoyed today's program as much as I do. See you around in the Future Science Prize Week. Thank you so much.